Welcome back to Science and Slumber. Tonight, we're going on a slow, soothing journey through our own cosmic neighborhood. We are going to ask a question that has been whispered in the quiet moments for as long as we have looked up at the night sky. In the vast, silent courtyard of our solar system, are we truly alone? It sounds like a simple question, with a simple yes or no answer, but the deeper you fall into it, the more it unfolds, becoming a story not just about other worlds, but about our own. It is a question that leads us through canyons of red dust, beneath oceans of ice, and into rains of liquid methane. If you have a moment before you drift away, you can tap the like button, and maybe subscribe. It quietly helps this sleepy little channel to grow, reaching others who might be looking for a little peace and wonder in the quiet hours. So now, settle in. Get truly comfortable. Let your body feel heavy and supported, and let your breathing find its own easy rhythm. Allow the words to wash over you, like the slow and patient light from a distant star, a message that takes its time and asks for nothing in return. Our search for life in the great dark expanse begins in the only place it can, with the life we already know, right here. Before we look out into the darkness between the stars, we must first look down at the ground beneath our feet. Before we call our world a planet, let us think of it as a garden. A vast, impossibly intricate garden, floating in a cosmic sea. It is the only one we know, the blueprint from which all our questions about life begin. Every garden needs three simple things to flourish: the right soil, a source of water, and a gentle, steady light. The soil of our garden is the world itself. It is the rich, dark dust of exploded stars, gathered over billions of years. It is the element carbon, a miraculous atom with four empty hands, always ready to link with others, to build the long, complex chains that form the backbone of life. It is nitrogen and oxygen and phosphorus, all the humble ingredients scattered in the rocks and stirred into the seas. This is the substance of life, the clay from which every leaf, every fin, every beating heart is sculpted. It is not rare in the universe, this cosmic dust. It is everywhere. But like seeds in a packet, it is just potential, waiting for the right conditions to awaken. Then there is the water. In our garden, water is everything. It is the great facilitator, the medium where the chemistry of life can happen. Imagine it as the gentle hand that stirs the pot, allowing the ingredients in the soil to meet, to dance, to combine. Liquid water is a magical substance. It can hold warmth, dissolve nutrients, and carry them from one place to another. On Earth, it fills the great basins of the oceans, a shimmering blue engine of life. It rises into the air, forming clouds that drift like soft white ships across the sky. It falls as rain, a cool and cleansing blessing that nourishes the land. It flows in rivers, carving canyons and building deltas. It flows through our own veins. It is the lifeblood of the garden, the single most important ingredient. Without it, the seeds of carbon would lie dormant forever. And finally, a garden needs a light. Not just any light, but a patient, reliable one. Our sun is that light. It is a star, but from here it feels like a perfect cosmic lamp hung at just the right distance. Its warmth is gentle enough to keep our water liquid, not so fierce that it boils away into space, not so faint that it freezes into a world of solid ice. It provides the energy that fuels nearly every living thing. Plants drink in its light, turning it into life, and that life then feeds other life, a cascade of energy that begins nearly 93 million miles away. This star of ours is also stable. It doesn't pulse or flare with violent, unpredictable rage. It simply burns with a quiet, steady dependability that has lasted for billions of years, giving our garden the immense, uninterrupted time it needed to grow. Soil, water, and light, carbon chemistry, liquid water, and a stable star. In other words, life as we know it is a delicate recipe, requiring a foundation of willing elements, a river of flowing water to mix them, and a patient fire to gently warm them. What this really means is that our world is a rare and gentle sanctuary, a perfect and fragile balance of substance, solvent, and energy. This is our definition of life, because it is the only one we have ever seen. It is the standard by which we will measure every other world we visit. But this perfect recipe is only half of the story. That perfect balance of soil, water and light is not just a matter of having the right ingredients, but of having them in the right place. Our garden is not just well tended, it is perfectly located. Astronomers have a simple, almost cozy name for this concept, the Goldilocks zone. It's the idea that for a planet to have liquid water, it can't be too hot and it can't be too cold. It must be just right. Imagine you are sitting by a vast, crackling campfire on a clear, dark night. The fire is the sun, a great roaring sphere of warmth and light in the center of the clearing. If you sit too close, the heat is overwhelming. Your clothes feel as if they might catch fire. The air shimmers, and any water in a cup beside you would quickly hiss and turn to steam, vanishing into the night. This is the fate of planets like Mercury and Venus, huddled too close to the solar flame. Venus, though similar in size to Earth, is a world scorched, its atmosphere a thick, suffocating blanket that has trapped the sun's heat in a runaway greenhouse effect, creating temperatures hot enough to melt lead. Any water it may have once had has long since boiled away, a ghost of a lost ocean. Now, imagine you move too far from the campfire. You back away, past the comfortable ring of warmth, out into the chill of the deep woods. The fire is still beautiful, a bright, distant jewel, but its heat can no longer reach you. The air grows sharp and cold. A frost begins to form on the grass. The water in your cup would turn solid, freezing into a useless block of ice. This is the realm of the outer planets, the gas giants and their frozen moons. Worlds like Jupiter and Saturn exist in a permanent, deep winter. Their water is not the flowing, life-giving liquid of our oceans, but a hard, unyielding mineral, locked away in icy shells and frozen crystals, as inert as rock. But right in between the scorching heat and the deep freeze, there is a gentle, habitable ring, a comfortable, life-sustaining distance from the fire. This is the Goldilocks zone. It is the place where you can sit and feel the warmth on your face without being burned, where the light is bright enough to see by, and where the water in your cup remains a gentle, life-giving liquid. Earth orbits within this perfect temperate band. Our planet found the one spot in our vast solar system where the sun's energy is perfectly balanced enough to power a world, but not enough to sterilize it. There's something quietly poetic about this idea. It suggests that habitability isn't a feature of a planet alone, but a relationship between a planet and its star. It is a slow cosmic dance. Our world has been circling this campfire at just the right distance for more than 4 billion years. This incredible stability has allowed life not just to begin, but to evolve, to grow complex, to fill every niche of the garden, from the deepest trenches of the sea to the highest mountain peaks. In other words, the location of our world is not an accident. It is the fundamental reason we are here. It is the gentle, life-permitting space that makes the soil and the water matter. We are children of a temperate zone, born of a perfect cosmic climate. This realization gives us a map for our search. It tells us where to look first for other gardens, other potential homes for life. We look for worlds that are also sitting at a comfortable distance from their own campfires. But even with the right ingredients and the perfect location, there is one more step. There is the moment a garden, once just soil and water, actually comes alive, and that is the quietest mystery of all. Even in a perfectly placed garden, with the richest soil and the purest water, life does not simply appear. There is a moment, a transition, so profound and mysterious that it lies at the very edge of our understanding. It is the bridge between the non-living and the living. Scientists call it abiogenesis. But we can think of it as the first spark in the water. Let us travel back in time to a younger Earth, long before the garden was green. Imagine a world still cooling from its fiery birth. The sun is weaker, the sky is a hazy orange, and the oceans are a warm chemical soup tinted brown with dissolved iron and minerals. There are no fish, no plants, no creatures of any kind. There is only rock, water, and air, all silently interacting under the light of the young Sunday. This ancient ocean is a vast, quiet kitchen. The ingredients are all there: the carbon atoms, the water molecules, the nitrogen, the phosphorus, all swirling in a planetary-scale mixture, warmed by the gentle heat from volcanic vents on the seafloor. For millions upon millions of years, this is all that happens. The tides ebb and flow, volcanoes erupt, adding new chemicals to the mix. Lightning cracks across the sky, its energy zapping the simple molecules in the air, causing them to break apart and reform into slightly more complex shapes. Comets and asteroids, remnants from the solar system's construction, fall from the sky, delivering their own cargoes of water and organic compounds. The kitchen is slowly being stocked with more and more interesting ingredients. Simple amino acids, the building blocks of proteins, begin to form. Fatty acids, the fatty acids, the precursors to cell membranes, float on the surface like an oily sheen. None of these things are alive. They are just complex chemicals, inert and without purpose, like letters of an alphabet scattered on a table. But then, somewhere in a quiet, protected corner of this worldwide ocean, perhaps in a shallow, sun-drenched tidal pool, or clinging to the mineral-rich surfaces of a deep-sea hydrothermal vent, something extraordinary begins to happen. The letters start to form words. The simple molecules, by sheer patient chance, begin to link together. Amino acids form chains. Fatty acids, due to their natural aversion to water, curl up into tiny hollow spheres, creating the first primitive bubbles, the first containers. Imagine one of these tiny bubbles, a microscopic sphere of oil, floating in the warm water. By chance, it happens to trap a few of those newly formed protein chains inside. This little bubble is not alive, but it is special. For the first time, there is an inside and an outside. It has created a tiny private laboratory, separate from the vastness of the ocean. Inside this protected space, the chemical reactions are a little different, a little more concentrated, and then comes the true miracle. One of the molecules trapped inside develops a strange and beautiful new trick. It learns how to make a copy of itself. This is the spark. It is the moment the chemistry becomes biology. The moment a collection of molecules begins to reproduce. It is not a dramatic event, no flash of light, no clap of thunder. It is a quiet, microscopic shift from passive chemistry to active replication. This first self-copying molecule is incredibly simple, fragile, and clumsy. Most of its copies are flawed, but the ones that are slightly better at copying themselves survive. And so, a new force enters the universe: natural selection. The words are now forming sentences, and the sentences are telling a story. In other words, life didn't erupt into being, it emerged, slowly and patiently, from the inherent creativity of chemistry. It was a gradual crescendo of complexity, a quiet, emergent property of a wet, rocky, sunlit world. What this really means is that life may not be a miracle in the sense of being an impossible supernatural event, but in the sense of being a profoundly beautiful and natural outcome of the laws of physics and chemistry. Given enough time and the right conditions, it's the moment the garden wakes up. With this understanding of our own awakening, we are finally ready to leave our garden behind. We can now lift our gaze and take our first step outward into the silent black soil of space, carrying our blueprint of life with us as a guide. Now, our journey truly begins. We rise from the soft green and deep blue of our world, a slow and graceful ascent. Imagine the feeling of letting go, of a gentle upward pull that lifts you from the familiar embrace of the ground. Below you, the garden shrinks, its continents and oceans resolving into a familiar swirling pattern of green, brown, white, and blue. You pass through the thin, wispy veils of the clouds, those floating ships of water vapour, and continue to climb. The brilliant, azure dome of the sky begins to deepen, its colour shifting from a friendly, welcoming blue to a darker, more solemn indigo, and finally to the profound and velvety black of space. Here, in this transition, the entire sensory world changes. The familiar sounds of the wind, the waves, and the distant hum of life fade away into an absolute and perfect silence. There is no air here to carry sound, only the vast, quiet emptiness. The warmth of the sun is still present, but it is a different kind of warmth now, a direct, unfiltered radiance on one side and a deep, penetrating cold on the other. You have left the gentle, moderated climate of the garden's atmosphere and entered a realm of pure extremes. You are floating in the space between worlds. Below you, Earth hangs like a magnificent living jewel. It is a beacon of light and colour in the immense darkness, a testament to the power of that delicate recipe of soil, water and sunlight. From this vantage point, you can see the thin, fragile shell of the atmosphere, a luminous, paper-thin blue line hugging the curve of the planet. That delicate layer is everything. It is the garden wall, protecting the life within from the harshness of space, holding in the warmth, the water, and the very air we breathe. To leave it is to understand, in a deep and visceral way, just how precious and precarious our living world island. We are now adrift in the cosmic sea, travellers in a darkness spangled with the distant, unblinking lights of stars. The sun is no longer a gentle lamp in the sky. It is a fierce, brilliant star, a blazing ball of thermonuclear fire, its power raw and untamed. This is the perspective we need to begin our search. We are no longer inhabitants of a world, but explorers of a system. Our first destination is not far. It hangs in the blackness ahead, a steady ochre-coloured point of light. It is a world that has haunted the human imagination for centuries, a place of myths and legends, of canals and ancient civilizations. It is the next world out from our own, our celestial neighbour. We turn our attention to it, this rusty lantern in the dark, and begin to move, gliding silently through the vacuum, leaving the blue marble of home behind us. The journey is quiet and slow. There is no sense of speed, only a gradual change in perspective. The Earth shrinks to a bright blue star behind us, while our destination slowly grows larger, its features becoming clearer. What was once a simple point of light resolves into a sphere, a world with texture and detail. We see its colour is not a uniform red, but a subtle tapestry of rust, orange and butterscotch, streaked with dark, mysterious markings and capped with brilliant white polar ice. There is a feeling of ancient stillness about this world. It seems to be holding its breath. What this really means is that we are approaching a place that has a deep and complex story to tell, a story that in many ways mirrors our own, but with a different, more sombre ending. We are arriving at the fourth stone from the sun, the planet Mars, and we are not just visiting a place, we are visiting a memory. As we draw closer to Mars, gliding into a slow, gentle orbit, we see it not as it is now, but as a ghost of what it might have been. Our eyes are not just cameras, but instruments of imagination, tuned to see the echoes of a past that whispers from the silent, ruddy dust. We are floating above a magnificent ruin, an abandoned kingdom of rust and rock, and every canyon and crater tells a story of a world that was once much more like our own. Imagine drifting over the surface of a vast terracotta desert on Earth, perhaps the sun-baked landscapes of Arizona, or the sweeping red sands of the Australian outback. You see canyons carved by ancient floods, dry riverbeds snaking for hundreds of miles, and the smooth, layered sediments of a lake that vanished millennia ago. Now, magnify that vision to the scale of an entire world. This is Mars. We glide over the Valles Marineris, a canyon system so vast that if it were on Earth, it would stretch from New York to California. This is no mere crack in the ground. It is a monumental scar, a feature that speaks to immense geological forces. But nested within its mighty walls, we see the unmistakable delicate tracery of smaller channels, features that look hauntingly like the tributaries of a river system, sculpted by flowing water. We drift onward, over the northern plains, a region smoother and lower in elevation than the cratered southern highlands. Scientists look at this vast basin and see the ghost of an ocean. They see what could be a primordial shoreline, a faint eroded boundary stretching for thousands of miles, marking the edge of a body of water that may have once held more liquid than our own Arctic Ocean. We pass over craters, the ancient pockmarks of cosmic impacts, but we notice something strange. In some of them, the debris fields look not like a dry, dusty explosion, but like a splash of wet mud, as if the asteroid struck a waterlogged surface, sending out a slurry that flowed and then froze in place. Perhaps the most evocative and beautiful feature we see is a vast, fan-shaped delta at the mouth of a crater named Jezero. It is an almost perfect replica of river deltas on Earth, like the Mississippi or the Nile. We can trace the path of the ancient river as it flowed into the calm waters of the crater lake. We see the main channel, and then how it fanned out, losing energy and depositing its load of sand and silt in delicate, overlapping layers. This is not a wild guess or a fanciful interpretation. It is the unambiguous signature of persistent, flowing liquid water. It is a geological postcard from a bygone era, a message that says, simply, a river once ran here. In other words, Mars is not just a dead planet, it is a fossil of a living one. It is a world that had, for a time, two of the most important ingredients for our garden, a rocky, mineral-rich soil and, most tantalizingly, abundant liquid water. What this really means is that billions of years ago, Mars may have been in its own Goldilocks zone, a warmer, wetter and more hospitable place. It was a world that had at least started down the same path as Earth. It had its own spring. To stand in a ruin on Earth is to feel a sense of melancholy and wonder for a civilization now gone. To orbit Mars is to feel that same sense, but for a biosphere, we are drifting through the skeletal remains of a world that might have been. The wind that now blows the thin, cold dust across its surface is a phantom sigh for the oceans that were lost, but a ghost is a memory of something that was once real. And so, we have to ask, if the water was here, could the spark of life have ignited in it? To find out, we need to go down to the surface, not in person, but through our slow and patient proxies. We must land in the dust and sift through the ruins. To explore this ancient, silent ruin, we cannot simply walk its surface. The air is too thin, the temperature too cold, the radiation too harsh. So we send extensions of ourselves, our robotic envoys, to be our eyes, our hands, and our scientific instruments. These are the rovers, the slow and patient wanderers of the Red Planet. They are not just machines of wire and metal. They are the embodiment of human curiosity, our hands reaching out across millions of miles of empty space to touch the dust of another world. Imagine a team of incredibly patient, meticulous archaeologists working in a vast, windswept desert, searching for the faint traces of a lost civilization. They cannot move quickly. Every step is deliberate. Every rock they examine is chosen with care. They work for years, decades even, in solitude, slowly and methodically piecing together a story from fragments of pottery and whispers of forgotten foundations. This is the work of the rovers. Spirit and Opportunity, the twin geologists who landed in 2004, were the pioneers. They were built to last for 90 days, but they became true planetary explorers, enduring for years. Opportunity, in particular, became a legend, a lonely, tenacious traveller who roamed for over 14 years, sending back postcard after postcard from a world of wonders, from tiny, iron-rich spheres, the scientists nicknamed blueberries, that could only have formed in water, to the rim of a vast crater called Endeavour. We can almost feel the quiet dedication of the scientists and engineers back on Earth, who would wake up each morning and go to work on Mars time, living their lives by the rhythm of a different world to guide their distant companions. Then came Curiosity, a mobile chemistry lab the size of a small car. It landed in Gale Crater, a place chosen specifically because it contains a towering 5-kilometre high mountain of layered sediment, Mount Sharp. This mountain is a history book, with each layer telling a story of a different Martian era. Curiosity's mission is to read that book. We can picture it now, a solitary, 6-wheeled explorer inching its way up the base of this alien mountain. It drills into rocks, scooping up the fine, reddish powder, and pulls it inside its belly to analyze in its onboard laboratory. It is tasting the planet, looking for the chemical building blocks of life, carbon, nitrogen, oxygen, the very ingredients that filled our own primordial oceans, and it found them. It found evidence of an ancient freshwater lake, a place so benign that if you could travel back in time, you could have safely drunk the water. Its companion, Perseverance, landed in Jezero Crater, that beautiful haunting river delta we saw from orbit. Its mission is even more focused. It is not just looking for habitable environments, it is actively searching for the fossilized signs of past life itself, biosignatures. It carries a sophisticated suite of tools, including a coring drill that can collect the most promising rock samples, seal them in pristine metal tubes, and leave them in a neat cache on the surface. These tubes are a message in a bottle for the future, waiting for a later mission to pick them up and return them to Earth, where our most powerful laboratories can study them. It is a slow, multi-generational act of scientific faith. In other words, these rovers are not just exploring Mars, they are conducting a planetary-scale forensic investigation. They are sifting through the crime scene of a lost world, looking for the fingerprints of biology. What this really means is that we are no longer just looking at Mars through telescopes and seeing a blurry red disk. We are there. We feel the crunch of the wheels on the gravelly terrain. We see the shadows stretch long in the thin, pinkish light of a Martian afternoon, and we share in the quiet, methodical patience of the search. The rovers have confirmed the story we read in the canyons and deltas. Mars was once a water world. But this only deepens the mystery. If the water is gone from the surface now, where did it go? And is it possible that somewhere, in some protected refuge, it still remains? The story of water on Mars is a tale of a world that lost its most precious resource. Billions of years ago, the planet's molten core cooled and solidified. When it did, the magnetic field that had protected its atmosphere from the harsh solar wind vanished. Without this invisible shield, the sun's energy slowly but surely stripped away the Martian air, molecule by molecule. As the atmosphere thinned, the pressure dropped, and the water on the surface simply evaporated, lost to the vacuum of space. The rivers dried up, the oceans vanished, and the planet transformed from a warmer, wetter garden into the cold, arid desert we see today. But not all the water was lost. A significant portion of it retreated, seeking refuge where the sun's stripping rays could not reach it. It became a hidden treasure, locked away in the planet's coldest regions. To find it, we must journey to the poles of Mars, to the vast, brilliant white caps of ice that crown the top and bottom of the planet. Imagine standing at one of Earth's poles, in the immense silent expanse of Antarctica or the Arctic. You are surrounded by a landscape of brilliant, blinding white, a seemingly endless sheet of ice and snow stretching to the horizon. The air is so cold it feels sharp in your lungs. There is a profound sense of stillness, of time held in suspension. Now, transport this feeling to Mars. We are floating over Planemborium, the northern polar cap. It is a spectacular sight, a swirling, spiral-shaped expanse of water, ice and frozen carbon dioxide, nearly 700 miles across. It is not just a flat sheet, but a complex, layered structure, like a gigantic stack of icy pancakes. These layers are a timeline. Each one represents a different era of Martian climate, laid down over millions of years, season after season, eon after eon. They are like the rings of a tree, or the layers of sediment in a lake bed. Just as our own ice cores on Earth tell us the story of our planet's ice ages, these Martian layers hold a frozen library of the planet's history. They contain trapped dust from ancient dust storms, chemical traces from volcanic eruptions, and, most importantly, a record of the water that once flowed and the atmosphere that once breathed. If we could drill down into this ice, we could read the story of Mars's slow transformation. But the polar caps are not the only place water is hiding. Radar instruments on our orbiting spacecraft have peered beneath the dusty surface and found something astonishing. Vast, buried glaciers of water ice, even at the middle latitudes. They are hidden just a few feet below the ground, protected from the thin atmosphere by a blanket of red dust. Imagine a desert on Earth, but just beneath the warm sand lies a thick, solid sheet of ice, a frozen reservoir waiting in the dark. This is a significant portion of Mars. There's something deeply hopeful about this discovery. It means that Mars is not entirely dry. The water is still there, a sleeping giant beneath the surface. What this really means is that the raw ingredients for life, at least the life we know, have not been completely erased. They have simply gone into hiding. This opens up a new and tantalizing possibility. Could something be sleeping in that ice? We think of ice as a tomb, a place of suspended animation. But on Earth, we find microbes that can survive, dormant, for thousands of years frozen in glaciers. Could the Martian ice be a sanctuary? A place where the last, most resilient remnants of a bygone biosphere are waiting, frozen in time, for the return of a warmer spring? And this leads to an even more profound question. Perhaps life on Mars didn't die out at all. Perhaps, like the water, it simply retreated. It journeyed downward into the warmer, more protected regions deep beneath the surface. And maybe, just maybe, it is still there, breathing softly in the dark. Our search for life on Mars now takes us from the visible world of canyons and ice caps to the invisible world of the atmosphere. We are no longer looking for fossils in the rock, but for a faint chemical whisper in the air. The Martian atmosphere is incredibly thin, less than 1% the density of Earth's, a mere ghost of what it once was. For the most part, it is a simple, predictable mixture of carbon dioxide with traces of nitrogen and argon. But over the last 2 decades, our orbiters and rovers have detected something that shouldn't be there: faint, fleeting, and mysterious puffs of methane. On Earth, methane is a gas intimately connected with life. It is produced by the metabolic processes of countless microorganisms, from the microbes in the guts of cows and termites to the bacteria that thrive in oxygen-poor environments like swamps and wetlands. It is the chemical signature of digestion, of decomposition, of life at work. It is a biosignature. So when we detected methane on Mars, even in tiny, almost imperceptible amounts, it was a profound and exciting discovery. Imagine you are in a vast, ancient, and perfectly silent library. For centuries, no one has walked its halls. The air is still, thick with the scent of old paper and dust. You believe the library is completely empty. But then, one day, you catch a faint, momentary scent, a whisper of perfume, or the smell of a recently extinguished candle. It is there for just a moment, and then it is gone. But the scent is a clue. It tells you that something is not as it seems. Your quiet, empty library may not be so empty after all. The methane on Mars is like that fleeting scent. The mystery deepens when we look at how the methane behaves. It doesn't just hang in the atmosphere uniformly. It appears in specific locations, at specific times of the year, and then it vanishes as quickly as it came. The Curiosity rover, for instance, has measured a background level of methane that seems to rise and fall with the seasons. And on a few occasions, it has detected sudden dramatic spikes, where the concentration of methane shoots up by a factor of 10 or more, only to disappear a few weeks later. These are the puffs, the plumes of gas that seem to be burped out from specific localized spots beneath the ground. Now, there are ways to produce methane that have nothing to do with life. Certain geological processes, involving the interaction of water, rock, and heat, can also release methane. This is the non-biological explanation. It could be that deep underground, pockets of water are reacting with olivine minerals in the Martian crust, a process called serpentinization, which slowly generates methane that gets trapped. Periodically, cracks and fissures open up, and this trapped gas escapes to the surface in a sudden puff. This would be a fascinating discovery in its own right, as it would point to active geological and hydrological processes still happening on Mars today. But there is the other, more wondrous possibility. The possibility that the methane is the faint metabolic breath of microbial life. We can imagine tiny, resilient communities of methanogens, microbes that consume hydrogen and carbon dioxide and release methane as waste hiding deep beneath the Martian surface. They would live in the dark, in pockets of salty liquid water, shielded from the harsh radiation, drawing their energy not from the sun, but from the simple chemical reactions in the rocks around them. They would be living a slow, quiet existence in the Martian underworld. Periodically, as the seasons change and the ground warms, fissures might open up, allowing their gaseous waste product to seep to the surface, where our sensitive instruments can just barely detect it, In other words, the methane is a fork in the road of our understanding. One path leads to a story of a geologically active Mars, a world that is not quite dead. The other path leads to a biologically active Mars, a world that is not quite sterile. Both are compelling. What this really means is that Mars is holding its secrets close. The scent in the library is real, but we do not yet know its source. Is it the ghost of a chemical reaction, or the living breath of a hidden ecosystem? The answer is likely buried deep beneath the dust. To find it, we will need to drill, to go down into the planet's secrets. But for now, our journey must continue outward. We leave the red world and its lingering, tantalizing mysteries behind, and venture into the deeper, colder darkness of the outer solar system. We pull away from Mars, its rusty, cratered face shrinking behind us until it is once again a bright, ruddy star in the rearview mirror of our journey. Our trajectory now takes us into a vast, uncharted territory, a great dark ocean of space that separates the inner, rocky planets from the colossal gas giants of the outer realm. This is the asteroid belt. Imagine driving at night through a familiar, well-lit countryside. The worlds of Mercury, Venus, Earth and Mars are like small towns, their lights relatively close and their paths well understood. But now, we have left the last town behind. The road signs have vanished, and we are entering a vast, dark forest. The asteroid belt is not a crowded, chaotic gravel pit, like it is often portrayed in movies. It is a place of immense emptiness. The asteroids themselves, the millions of pieces of rock and metal that orbit here, are separated by vast distances. If you were standing on one, you would likely not even be able to see the next. But collectively, they represent a ghost. They are the leftovers of creation, the building blocks of a planet that never was. As we drift through this silent, sparsely populated wilderness, the character of our journey changes. The sun, which was a brilliant, dominant presence in the inner solar system, is now much farther away. Its light is noticeably dimmer, softer. It has become a distant, powerful beacon rather than an all-encompassing furnace. The warmth that bathed Earth and scorched Venus is now a faint caress, and the ambient temperature of space drops precipitously. We are entering a realm of profound and enduring cold. This is more than just a physical transition, it's a conceptual one. We are leaving the region where the Goldilocks principle, as we first understood it, makes sense. We are travelling far beyond the campfire's comfortable ring of warmth, into a domain where liquid water on a planet's surface should be an impossibility. According to our initial blueprint for life, soil, sunlight, and liquid water, this entire region of the solar system should be a barren, frozen desert, utterly hostile to life as we know it. We are entering a place where the rules of the garden seem no longer to apply. The journey across the belt is long and meditative. We glide past primordial rocks that have been tumbling in the dark for 4.5 billion years, unchanged since the dawn of the solar system. They are like ancient, gnarled trees in the forest, silent witnesses to the entire history of our cosmic neighborhood. Some are dark and carbon-rich, carrying the same organic molecules that may have seeded the early Earth. Others are bright and metallic, the exposed iron cores of protoplanets that formed and were then shattered in ancient collisions. Each one is a time capsule, a message from the past. There is a sense of humility that comes with this passage. We are crossing a boundary, not just in space, but in our own expectations. We are heading for a place where our Earth-centric ideas about life might prove too narrow, too limited. Life, if it exists out, here in the cold and the dark, must play by a different set of rules. It must find its energy not from the distant fading sun, but from some other, more mysterious source. Finally, after a long and quiet transit, we emerge from the belt, and there before us, hanging in the blackness like a celestial emperor, is the king of the planets. Its sheer scale is breathtaking, a world so vast it could swallow every other planet whole. But our destination is not the great giant itself. We are here to visit its court, to explore the dozens of small worlds that dance around it like loyal attendants, and one in particular catches our eye, a small, unassuming pearl gleaming in the faint sunlight. We have arrived in the dominion of Jupiter, The planet itself dominates our view, a colossal, majestic sphere of swirling gas and storms. It is a world of breathtaking violence and scale, a symphony of chaos painted in bands of cream, orange, and brown. The Great Red Spot, a storm larger than our entire Earth, churns in its southern hemisphere like a baleful, unblinking eye. Jupiter is not a place, it is a force of nature. It is the gravitational anchor of our solar system, a protective older brother whose immense gravity shields the inner planets from a constant barrage of comets and asteroids. It is a king, ruling over a complex and fascinating kingdom of its own. Its court is a miniature solar system, a retinue of over 80 moons, each one a unique world in its own right. Some are captured asteroids, tumbling erratically in the outer reaches of Jupiter's grasp. Others are giants themselves, like Ganymede, the largest moon in the solar system, a world bigger than the planet Mercury, with its own magnetic field. There is volcanic Io, the most geologically active body we have ever observed, its surface a hellish landscape of sulphurous plains and constantly erupting volcanoes, a world tortured by the relentless push and pull of Jupiter's gravity. But our gaze is drawn past these more dramatic courtiers. We are looking for something quieter, something that at first glance seems much less remarkable. We are looking for Europa. It hangs in space, a small white globe, shining with the serene, placid light of reflected sunshine. Compared to the turbulent, colourful chaos of Jupiter or the fiery drama of Io, Europa seems almost plain, a smooth, ivory-coloured ball, crisscrossed with a delicate network of faint reddish lines. It looks like a perfectly polished marble or a cue ball that has just begun to crack with age. There is a deep and profound stillness about Europa. From a distance, it appears to be a world frozen in time, an inert ball of ice orbiting its colossal parent. It is far, far outside the traditional habitable zone. The sunlight that reaches it is more than 25 times fainter than the light that bathes our Earth. The surface temperature hovers at a staggering 260 degrees below 0 Fahrenheit. At this temperature, water ice is not soft like snow. It is as hard and unyielding as granite. By all the rules we have established, Europa should be a dead world, a place where the story of life could never even begin. Yet, this unassuming moon is arguably the most compelling and tantalizing target in our entire search for life beyond Earth. Its bland, quiet appearance is a mask, a frozen veil that hides a secret of unimaginable proportions. We are drawn to it not for what we see, but for what we have inferred is hidden beneath its deceptively placid surface. The story of Europa is a story of a hidden world, a place where the rules of the garden are rewritten in a dark and mysterious way. What this really means is that our journey has brought us to a place that challenges our most basic assumptions. We thought life needed the direct, gentle warmth of a star. But here, in the cold, outer reaches of the solar system, we are about to discover a new source of energy, a different kind of fire. In other words, Europa teaches us that the concept of a habitable zone might be more flexible than we ever imagined. The campfire of the sun may not be the only source of warmth in the cosmic wilderness. There can be other, more secret hearths. To understand Europa's secret, we must move closer. We must descend from a high orbit and drift low over its strange, icy and beautifully fractured surface. We must read the story written in its scars. We descend, leaving the grand, panoramic view of the Jovian system behind, and let Europa fill our entire field of vision. The smooth white marble we saw from a distance resolves into a landscape of breathtaking strangeness and complexity. We are now gliding just a few miles above its surface, close enough to see the fine details of this frozen world. The feeling is one of skating over a vast, endless and utterly alien ice rink under the dim, silvery light of a distant Sunday. The first thing we notice is that the surface is incredibly smooth on a large scale, and remarkably young. There are very few impact craters. On a world like our moon, or Mercury, the surface is saturated with the craters of billions of years of cosmic bombardment. The fact that Europa is so clean and unblemished is a profound clue. It tells us that the surface is not ancient and static, it is being constantly renewed from below. It is as if the ice rink is being periodically resurfaced by a celestial Zamboni, covering over the old marks and making it smooth again. This is the first hint that Europa is not a dead solid ball of ice, but a dynamic, geologically active world. Then, our attention is drawn to the most striking features of this landscape: the scars. The surface is covered in a dense, intersecting network of cracks, ridges and bands that stretch for thousands of miles. These are the faint reddish lines we saw from afar. Up close, they are monumental structures. We drift along a double ridge, two parallel mountain ranges of ice with a valley running down the middle, a feature that runs for hundreds of miles, as straight as if drawn with a ruler. We cross over vast dark bands, areas where the crust seems to have been pulled apart, with new, darker material welling up from below to fill the gap. And everywhere there are the simple cracks, the lineae, intricate and fine like the crazing on old pottery. The colour of these features is a mystery in itself. The ice of Europa is mostly pure, white water ice, but these cracks and bands are tinted with a reddish-brown non-ice material. Scientists are not entirely sure what it is, but the leading hypothesis is that it is salts and minerals, perhaps mixed with organic compounds, that have been dredged up from whatever lies beneath the ice, and then blasted by the intense radiation that bathes the Jovian system. It is as if the world is bleeding, its internal chemistry staining the pristine white of its surface. Imagine a frozen lake on a cold winter's day. As the temperature changes, the ice groans and cracks. Water from below might well up and freeze, creating a dark, fresh scar on the white surface. Now, picture this process happening on a planetary scale, driven not by the changing of the seasons, but by a much more powerful and relentless force. Europa is constantly being squeezed and stretched by the colossal gravity of Jupiter. As it follows its slightly elliptical orbit, it moves closer to and then farther from the giant planet, and the gravitational pull flexes the entire moon. This process is called tidal heating. It is a constant, rhythmic massage that generates enormous friction, and therefore heat deep within Europa's core. In other words, these scars on the ice are the surface expression of a tremendous hidden energy. They are the cracks in the ceiling of a room where a great warm engine is constantly running. What this really means is that Europa generates its own heat. It does not need the sun's campfire. It has its own internal furnace, a secret hearth powered by the process, relentless gravity of its parent planet. This is the key that unlocks the greatest secret of this small, unassuming moon. And it points to the existence of something truly extraordinary, hidden just beneath this cold, fractured sky of ice. The evidence is all around us as we drift over this strange, frozen landscape. The youthful, crater-free surface, the colossal networks of ridges and cracks, and the undeniable presence of an internal heat source all point to one of the most staggering and hopeful conclusions in modern planetary science. The ice we are flying over is not the full story of this world. It is merely the crust, a shell, and beneath this shell of solid ice lies Europa's great secret, a vast, globe-spanning ocean of liquid salt water. Let us now leave the sunlit, irradiated surface behind and begin a journey of pure imagination. We find a place on the fractured ice sheet, perhaps a newly formed crack where the ice is thinnest, and we begin to descend. We sink through the ice, leaving the black, star-dusted sky of space behind us. The first few miles are through ice that is brittle and incredibly cold, harder than granite. It is a realm of absolute silence and stillness, the ice a translucent crystalline solid. Dim, filtered sunlight might penetrate this upper layer, creating a faint ethereal blue glow, a cathedral of deep, cold twilight. But as we continue our descent, a change begins to occur. The tidal heat generated by Jupiter's pull, which we saw expressed as cracks on the surface, is now a palpable presence. The ice is no longer a perfect rigid solid. It becomes warmer, softer, more plastic. It begins to behave less like rock and more like the flowing ice of a terrestrial glacier. We can imagine vast, slow-moving convection currents within the ice shell, with warmer ice from below rising and colder ice from above sinking. a process that could take thousands of years, but is the engine that constantly resurfaces the world above. We continue to sink, mile after mile, through this thick, slowly churning mantle of ice. The pressure is immense, and the darkness is now absolute. We have left the last vestiges of sunlight far above. And then, after a journey of perhaps 10, perhaps 20, perhaps even 60 miles, we break through. We emerge from the solid ceiling of ice into a realm of liquid. We are floating in the waters of a hidden, alien ocean. Try to feel the sheer scale and wonder of this place. We are in a body of water that completely encircles an entire world. The ceiling of our world is a shimmering, undulating layer of ice, its underside perhaps carved into canyons and mountains by the ocean currents. The floor, many miles below, is a bed of dark, silicate rock, the moon's true surface, and the ocean itself, it is a volume of water 2 to 3 times greater than all of Earth's oceans combined. It is a place of profound, eternal darkness and unimaginable pressure, and it is liquid. It is warm enough to be a flowing, dynamic chemical medium, thanks not to the sun, but to the constant gravitational kneading of Jupiter. This is the great revelation of Europa. It completely redefines our concept of a habitable zone. We have found a world that has, in abundance, the single most important ingredient for life, as we know it, liquid water. It is not on the surface where we expected to find it, but hidden away, protected from the cold and radiation of space by a thick insulating blanket of ice. In other words, Europa is a cosmic incubator, a celestial egg with a hard frozen shell and a life-giving liquid interior. What this really means is that we have found a second, entirely different way to build a garden in our solar system. You can place it near a star's gentle light, like Earth, or you can place it next to a gravitational giant and let its tidal forces create the warmth needed to sustain a hidden ocean. But an ocean, even a warm one, is not enough. Life needs more than just water. It needs energy and chemical nutrients, and in this sunless, primordial deep, there is only one place to find them. We must now continue our descent, sinking through the dark water toward the sea floor miles below. We sink now, deeper and deeper into the utter blackness of the European Ocean. The pressure builds to crushing levels, thousands of times greater than at the bottom of our own seas. The only light is the one we bring in our imagination, a soft, probing beam cutting through the inky alien water. We are descending into one of the most mysterious and inaccessible places in our solar system, a place where no sunlight has ever reached. On Earth, nearly all life depends, directly or indirectly, on the energy of the Sunday photosynthesis is the foundation of our entire biosphere. But here, in this eternal midnight, life would need to find another source of power. As we approach the seafloor, our light picks out a landscape of dark volcanic rock, perhaps covered in a fine silt of minerals that have settled over eons. It is a sterile, silent, and seemingly empty world, but then, in the distance, we see a faint, shimmering light. It is not a steady glow, but a flickering, dancing illumination, like a distant bonfire seen through a thick fog. We move toward it, and as we do, we begin to feel a change in the water. A gentle current begins to pull us forward, and the water itself grows warmer. We arrive at the source of the light and warmth, and what we see is a scene of both alien and deeply familiar beauty. Before us is a forest of towering, chimney-like structures, some rising hundreds of feet from the seafloor. They are jagged and black, like miniature twisted mountain ranges, and from their tops, a thick, black, superheated fluid billows out into the cold ocean water, like smoke from a factory smokestack. This is a hydrothermal vent. We have found the engine of the ocean floor. This is where the ocean water, seeping down through cracks in the rocky seafloor, comes into contact with the hot magma of Europa's interior, heated by that same tidal flexing that warms the whole moon. The water is superheated and infused with a rich cocktail of dissolved minerals and chemicals from the rock sulfur compounds, hydrogen, methane. This hot, buoyant, chemical-rich fluid then erupts back into the ocean, creating these incredible structures. On Earth, In the 1972nd, when humanity first explored the deep ocean, we discovered these same features along our mid-ocean ridges. And clustered around them, we found something that revolutionized our understanding of biology: thriving, vibrant ecosystems, completely independent of the sunday. Instead of photosynthesis, the life here relied on chemosynthesis. Bacteria and archaea, the most ancient forms of life on our planet, were feeding directly on the chemical energy of the compounds spewing from the vents, particularly hydrogen sulfide. They were eating rocks and water, powered by the planet's internal heat. And these microbes formed the base of a food chain that included giant tube worms, ghostly white crabs, and strange pale fish, all living in the crushing dark. So now, in our mind's eye, we turn our light onto the base of these Europan vents. We imagine the same possibility. The rock here is likely rich in the same sulfides and minerals. The water is a flowing medium. The energy is abundant. This is the one place in this entire hidden ocean that has all the ingredients for a garden, a dark garden, thriving not on light but on chemistry. We can imagine the rock around these vents covered in a thick, slimy mat of alien microbes, the first, simplest life forms of this sunless world. Perhaps strange, slow-moving creatures graze upon these microbial mats, and larger, ghost-like predators drift silently in the darkness, hunting by feel or by sensing the chemical trails of their prey. In other words, these hydrothermal vents are deep-sea fireflies, oases of light and energy in an otherwise dark and sterile desert. They are the campfires of the deep, around which a completely alien biosphere could be huddled. What this really means is that life on Europa is not just a vague, abstract possibility. We have a specific, testable hypothesis about where it might be and how it might work. It would be a second, independent Genesis, a Life 2.0, born in the dark and powered by the heart of a moon. This breathtaking possibility, a living ocean hidden under ice, changes everything. It tells us that the potential for life in the solar system is not limited to the sunlit surfaces of rocky worlds, and Europa is not the only moon that seems to be hiding such a secret. Our journey must now take us to the next great gas giant, to see a world that is not just hiding an ocean, but is actively telling us about it. We ascend from the imagined depths of Europa, leaving its dark, secret ocean behind. We rise back through the miles of ice, emerging once more into the silent vacuum of space. Jupiter and its court recede as we continue our journey outward, moving deeper into the cold and the dark. Our next destination is perhaps the most visually stunning and beloved object in the entire night sky. It is the ringed jewel of the solar system, Saturn. The journey from Jupiter to Saturn is another vast, quiet passage through the emptiness. The sun has shrunk even further, now appearing less like a disk and more like an intensely brilliant star, its light casting long, faint shadows. The sense of being far from the central fire is now profound. But ahead of us, our destination grows, resolving from a point of light into a celestial masterpiece. Saturn is a softer, more subtle beauty than Jupiter. Its colours are more muted, gentle bands of butter yellow, pale gold, and hazy cream. It has a serene, stately, almost peaceful presence, a gas giant that seems less like a raging king and more like a wise old emperor. And then, of course, there are the rings. They are the defining feature, a structure of such impossible, ethereal grace that they look like an artist's creation rather than a natural phenomenon. From a distance, they appear as a solid, shimmering disk, tilted at a jaunty angle, but as we draw closer, we see that they are not solid at all. They are composed of billions of individual particles of almost pure water ice, ranging in size from tiny dust specks to chunks as large as a house, each one orbiting Saturn in its own perfect circular path. We glide over them, a vast, flat, shining river of ice, so thin that if you scaled the system down, the rings would be proportionally thinner than a sheet of paper. Like Jupiter, Saturn is the lord of its own miniature solar system of moons. It has over 80 of them, a diverse and wondrous collection of worlds. We pass by the giant Titan, an enigma shrouded in a thick orange haze, which we will visit later. We see the strange, two-toned Iapetus, half bright as snow and half dark as asphalt. We see Mimas, with its one enormous crater that gives it the uncanny appearance of a science fiction battle station. These are all worlds with their own stories, their own secrets. But our focus is drawn to a much smaller, more humble moon, nestled within the bright, ethereal glow of Saturn's E-ring. It is a tiny world, only about 300 miles in diameter, small enough to fit comfortably within the borders of Arizona. From a distance, it is almost invisible against the glare of the rings. But as we approach, we see that it is the brightest, most reflective object in the entire solar system. Its surface is a brilliant, almost pure white, covered in a fine, powdery snow of fresh, clean ice. It shines with a pristine, almost startling intensity. This is Enceladus. Like Europa, it seems at first to be a simple, inert ball of ice. Given its tiny size, it should have cooled off and frozen solid billions of years ago. It should be a dead, silent, cratered rock. And yet, its bright, unblemished surface tells us the same story that Europa's did. This world is geologically alive. Its surface is constantly being repaved with fresh material from its interior. And again, we must ask the question, how? A world this small cannot possibly have enough radioactive material in its core to stay warm, and the tidal forces from Saturn, while present, should not be enough to generate the kind of heat needed to power a global resurfacing. There is a deep mystery here. This tiny, snow-white moon is an outlier, a puzzle that defied our models of planetary physics. It seems too small and too far from the sun to be anything but a frozen dead relic. Yet the evidence of its gleaming surface screams otherwise. What this really means is that our understanding of how worlds work is still incomplete. The solar system is still full of surprises. Enceladus is not just a moon, it is a lesson in humility, a reminder that our theories must always bend to the evidence. And the evidence on this little world is not just written in the ice. It is actively erupting into space, in one of the most spectacular and revealing displays in the entire solar system. We move in closer to Enceladus, skimming low over its pristine snow-white surface. The landscape is a mix of smooth, uncratered plains and regions of more complex grooved terrain, evidence of a dynamic geological past. The sheer brightness is astonishing. It's like flying over a vast field of freshly fallen snow on a sunny day, the reflected light almost blinding. We make our way towards the moon's southern hemisphere, where our instruments have detected a strange and unexpected thermal anomaly. The south pole of this tiny frozen world is inexplicably warm. As we approach, we see them. Etched into the ice of the south polar region is a series of 4 long parallel cracks, like the stripes of a tiger. They are about 80 miles long, spaced roughly 20 miles apart, and they glow with a faint bluish tinge. These are the famous tiger stripes of Enceladus, and they are not just cracks, they are active vents. Because from these fissures, in a display of breathtaking celestial beauty, erupt colossal plumes of water vapor and ice particles. Imagine standing in a silent, frozen landscape on a bitterly cold winter's night, and suddenly, the frozen river beside you erupts into a series of magnificent, shimmering geysers. That is what we are witnessing here. Great, towering jets of fine, glittering ice crystals are being blasted hundreds of miles out into space, moving at supersonic speeds. They are not violent, explosive eruptions, but a continuous, graceful, almost silent spray, like a cosmic fountain. The material catches the faint, distant sunlight, and the plumes form a brilliant, diaphanous halo around the moon's southern pole. It is a spectacle of such serene and unexpected majesty that it feels like a dream. This is the source of Enceladus's pristine brightness. The moon is constantly dusting itself with its own fine, icy snow, which falls back onto its surface, covering any craters or blemishes, keeping it forever young and clean. It is also the source of Saturn's entire E-ring. This one tiny moon, with its incredible polar geysers, is spewing enough material into space to create and sustain one of the largest structures in the solar system. But the beauty of this display is surpassed by its profound scientific meaning. We are watching a world actively and continuously exhaling its interior into space. This is not a theoretical inference, like the ocean of Europa, which we believe exists based on surface clues. This is direct, undeniable evidence. These geysers are originating from a body of liquid water hidden beneath the ice. Enceladus, like Europa, has a subsurface ocean. The tiger stripes are cracks in the ice shell that reach all the way down to this hidden sea, and the pressure from within is forcing the water out into the vacuum of space, where it instantly freezes and crystallizes into this beautiful shimmering spray. There's something incredibly poetic about this. We can think of it not as a geological process, but as the planet breathing. A slow, rhythmic exhalation, a sigh of water vapor into the void. It is a generous and revealing act. Unlike Europa, which holds its secrets close, locked away beneath miles of solid ice, Enceladus is offering its heart to us. It is broadcasting the composition of its hidden ocean into space for anyone or anything to sample. What this really means is that our search for life has just been given an incredible gift. We don't have to imagine drilling through a thick ice shell to find out what's in the water. All we have to do is fly through these plumes and catch the material as it sprays out. It is a direct line, a free sample, from an environment that could potentially harbour life. And that is exactly what we did. We sent a robotic messenger to fly through these celestial fountains and to taste the waters of another world. The story of our encounter with these incredible plumes is the story of a brave and faithful robotic explorer named Cassini. For 13 years, this remarkable spacecraft orbited Saturn, a robotic emissary from Earth that transformed our understanding of the entire Saturnian system. It was a mission of epic proportions, a slow and patient dance among the giant planet, its rings and its dozens of moons. And one of its most daring and revelatory acts was to fly directly through the geysers of Enceladus. Imagine being the mission controller back on Earth, making the decision to send your billion-dollar spacecraft, your life's work, hurtling at thousands of miles per hour through a dense, icy jet erupting from the surface of an alien moon. It was a maneuver of incredible precision and courage. On several occasions, Cassini altered its graceful orbit and made a series of low passes over Enceladus's south pole, its instruments wide open, ready to taste the material spraying out from the tiger stripes. It was the cosmic equivalent of putting your hand out to catch the falling snow. The spacecraft was not tasting in the human sense, of course. It was using a sophisticated instrument called a mass spectrometer, which could analyze the chemical composition of the tiny ice grains that entered it. As Cassini flew through the plumes, these microscopic particles of frozen ocean water slammed into its detector plate, instantly vaporizing. The instrument then sorted the resulting gas, molecule by molecule, weighing them to determine exactly what they were made of. It was a direct chemical analysis of an alien ocean, conducted from millions of miles away, and what it found was astonishing. The first and most important discovery was that the plume was almost entirely water. But it was not pure distilled water. It was salty. Cassini detected simple salts, like sodium chloride table salt, which confirmed that the hidden ocean was not a pocket of melted ice, but a vast body of liquid water that was in direct contact with a rocky, mineral-rich core, just like the oceans of Earth. This was a critical piece of the puzzle, as that interaction between rock and water is what creates the chemical disequilibrium, the raw potential, that life needs. But it found much more than just salt. Inside the ice grains, Cassini detected a treasure trove of organic molecules, not life itself, but the building blocks of life. It found simple compounds like methane, carbon dioxide, and ammonia. And it found more complex organic molecules, chains of carbon and hydrogen, the very kind of material that forms the basis of all life we know. The kitchen, it seemed, was fully stocked. And then came the final, most breathtaking discovery. On its last and deepest dive through the plumes, Cassini tasted molecular hydrogen. Hydrogen gas is not something that hangs around for long. It is highly reactive. To find it in the plumes meant that it was being actively produced, right now, deep within Enceladus, and the most likely source of that hydrogen is the very same process we imagined at the bottom of Europa's ocean. hydrothermal vents. The hydrogen is a chemical byproduct of the reactions between hot rock and liquid water on the seafloor. On Earth, molecular hydrogen is a delicacy for certain kinds of microbes. It is pure, high-quality chemical energy. It is food. So, to find it pouring out of Enceladus was like finding a fully stocked, powered-up kitchen with a sign on the door saying, "Free lunch." What this really means is that Enceladus has everything. We have confirmed a liquid water ocean. We have confirmed it's in contact with a rocky core. We have found the key organic building blocks. And now, we have found a confirmed source of chemical energy, a viable food source for a potential ecosystem. In other words, this tiny, shining moon, once thought to be a frozen, dead world, has leapt to the very top of our list of promising places to search for life. It is not just a maybe, it is a world that is actively advertising its own habitability. But the solar system has more surprises in store for us. Our journey now takes us to another of Saturn's moons, a world that is perhaps the strangest, most hauntingly familiar place we will ever visit. We pull back from the shimmering, life-giving plumes of Enceladus and turn our attention to the true giant in Saturn's court. It is the second largest moon in the entire solar system, a world larger than the planet Mercury. It is the only moon with a thick, substantial atmosphere. From space, it is a featureless, hazy orange-brown ball, an opaque and mysterious orb that hides its surface completely from our view. This is Titan. Our journey to Titan is a journey to a stranger shore, a place that feels like a distorted reflection of our own Earth, seen through a strange, amber-coloured glass. As we begin our descent, we plunge into its atmosphere, a thick, soupy mixture of nitrogen and methane, far denser than Earth's. For a long, slow passage, we see nothing but a uniform, deep orange haze. The sunlight struggles to filter through this thick smog, and the light that reaches the surface is 1,000 times dimmer than a sunny day on Earth, a permanent, hazy, deep twilight. Then, as we break through the lowest cloud layers, a landscape of stunning and eerie familiarity emerges below us. We see coastlines, we see branching dendritic river channels. We see vast, dark, placid seas. There are mountain ranges and rolling fields of dunes. It looks, for all the world, like a primordial, untouched version of Earth. The probe Huygens, a small lander that was part of the Cassini mission, gave us our only glimpse from the surface. In 2005, it drifted down on its parachute through this haze and landed in a dry riverbed. The images it sent back were of a flat, pebble-strewn plain stretching to a hazy horizon, a scene that could have been a desert in Arizona, were it not for the alien, orange sky. But here is the profound, mind-bending twist of Titan. Everything we are seeing, every feature that looks so familiar, is made of a completely different set of materials. The mountains are not made of rock, but of solid frozen water ice, which is so cold here at nearly 300 degrees below 0 Fahrenheit that it is as hard as granite. The riverbeds are not carved by water, but by a liquid that does not exist in nature on Earth, liquid methane. The vast, dark seas are not filled with salt water, but with liquid ethane and methane. And the soft, dark sand that forms the endless dunes is not made of silicate minerals, but of solid, hydrocarbon particles that have rained out of the atmosphere over millions of years. This is a world that runs on a completely different chemical system. It is an alien Earth, where water plays the role of rock, and liquid methane plays the role of water. It is a place that follows the same geological and atmospheric rules as our planet erosion, weather, a liquid cycle but with a radically different chemical toolkit. It is a stunning example of convergent evolution on a planetary scale. The same patterns emerge, but the substance is utterly different. What this really means is that we have found a place that forces us to expand our definition of a habitable world in a new and even more profound way. Europa and Enceladus taught us that life might exist without sunlight, powered by internal heat. Titan asks a much deeper question: does life even need liquid water? It is the one ingredient we have held as sacrosanct, the one non-negotiable component for life as we know it. But here, before us, is a world with a stable, abundant liquid on its surface, a liquid that can act as a solvent, a medium for chemistry to occur. It's just not water. In other words, Titan is a laboratory for exploring the possibilities of truly alien life. It is a journey to an alternate reality, a what-if scenario played out on a planetary scale. We are standing on the shore of a methane sea, looking out at a horizon where a hydrocarbon rain might be falling from an orange sky, and we have to ask one of the most exciting questions in all of science. Could something be swimming in that sea? Let us linger here, on this strange and haunting shore. Let us take a moment to truly immerse ourselves in the sensory experience of Titan. We are standing on the edge of a great dark sea called Kraken Mare, a body of liquid larger than all of Earth's Great Lakes combined. The ground beneath our feet is not sand or rock, but frozen, solid water ice, as hard as concrete, and coated in a dark organic sludge that has settled out of the atmosphere over eons. The air is thick, cold and still, with a faint, acrid smell like a gas station or a chemical plant. The sky above is a permanent, gloomy, deep orange twilight. The sun is a distant, hazy spot, its light diffused and scattered by the thick, nitrogen-methane smog. It provides very little warmth. The temperature is a steady, numbing 290 degrees below 0 Fahrenheit. At this temperature, nitrogen gas itself is close to its condensation point. It is a cold beyond any winter's day on Earth. And then, it begins to rain. But this is not the rain we know. The drops are not small and fast, but large, slow, and almost oily. They fall with a lazy, deliberate pace, like beads of glycerin, due to the thick atmosphere and Titan's low gravity. This is liquid methane. It condenses in the high, cold atmosphere, forms thick, puffy methane clouds, and then falls as precipitation, just as water does on Earth. The rain darkens the icy ground, and you can see it pooling in small depressions before it begins to flow, gathering into tiny rivulets. We can follow these rivulets as they merge, forming a small stream that flows sluggishly over the hard, icy bedrock. This stream of liquid natural gas continues to grow, joining with others, until it becomes a true river, carving a channel through the landscape. We can see the erosion in action, the slow, patient work of a flowing liquid shaping a world. The river carves canyons, builds deltas, and finally empties into the vast, dark expanse of the methane sea. We stand on the shoreline and watch waves, slow and syrupy, lapping against the frozen coast. Out on the sea, the Huygens probe detected features that looked like wind-whipped waves, a clear sign of an active dynamic liquid surface interacting with the atmosphere. There is weather here. There are seasons. There is a complex planet-wide liquid cycle, a methanological cycle, that is a perfect, albeit much colder and slower, analogue to Earth's water cycle. Methane evaporates from the seas, forms clouds, falls as rain, carves rivers, and flows back to the seas. There is something profoundly unsettling and beautiful about this scene. It is so familiar in its form, yet so utterly alien in its substance. We are witnessing a parody of Earth, a world that took a different chemical path. It is a place that demonstrates that the physical processes that shape a planet are universal, but the materials they have to work with can be dramatically different. What this really means is that Titan is the ultimate test of our imagination. It presents us with a complete, functioning, and stable environment that has all the apparent prerequisites for life: a thick atmosphere for protection, a stable liquid for chemistry to occur in, and an abundance of complex organic molecules. It simply lacks the two things we thought were most essential: significant heat and liquid water. In other words, we are confronted with the most fundamental question in astrobiology. Is life a specific phenomenon, tied forever to the unique properties of liquid water and carbon chemistry in a warm environment? Or is life a more general, more flexible principle, a process that can adapt and arise in any sufficiently complex and stable chemical environment? Titan is the crucible where this question will be answered. It forces us to contemplate a form of life that is not just a little different from us, but one that is profoundly, fundamentally alien. Here on the shores of Titan's methane sea, we must consciously let go of our earthbound prejudices. We must try to imagine a form of life that is not just a variation on our own theme, but an entirely different kind of song. We are searching for life not as we know it, or what some scientists have poetically called weird life. Let's begin with the most basic problem, the container. Life on Earth is contained within a cell membrane made of a lipid bilayer, a double-walled bubble of fatty molecules. This structure works perfectly in water. The lipid heads are attracted to water, and the tails are repelled by it, so they naturally form a stable self-sealing barrier that separates the inside of the cell from the outside world. But in a sea of liquid methane, a substance that is a non-polar solvent, a lipid bilayer would fall apart. It would dissolve. A water-based cell would be like a bubble made of salt trying to float in the ocean. So, a hypothetical titanian organism would need a different kind of container. Scientists have theorized the existence of an azotosome, a cell membrane made not of lipids, but of nitrogen-containing organic compounds, like acrylonitrile, which Cassini detected in Titan's atmosphere. Computer models suggest that these molecules could, in the cryogenic cold of liquid methane, self-assemble into a stable, flexible, and permeable membrane. It would be a different kind of bubble, one that is perfectly at home in a methane sea, capable of holding a pocket of alien biology within it. Next, consider the metabolism. Life is a process of taking in energy and building complex structures. On Earth, we do this by breathing oxygen, a highly reactive gas that is perfect for powering a warm-blooded, high-energy biosphere. There is no free oxygen on Titan. Its chemistry is what we call reducing, the opposite of Earth's oxidizing environment. So, life here would need a different kind of fuel. Perhaps it would react hydrogen with acetylene, another chemical known to exist on Titan. This reaction would release a small but significant amount of energy, enough to power a very slow, cold-adapted metabolism. This is the key to imagining Titanian life. It would be slow. Chemical reactions happen much more sluggishly at 300 degrees below zero. Life here would not be fast and frantic. It would be a slow, patient, and deliberate existence. Imagine a creature that lives its entire life over the course of thousands of years, its metabolism a slow glacial burn. Its movements, if it moved at all, might be imperceptible to our eyes. It might be more like a slowly growing crystal than a scurrying animal. What would it look like? Perhaps it would be something like a lichen, clinging to the hard, icy rocks of the sea floor, drawing its chemical energy from the slow interaction between the rock and the methane sea. Perhaps there would be free-floating organisms, like our plankton, that drift on the slow, syrupy currents of Kraken Mare, their bodies made of strange, waxy or plastic-like organic polymers. It is unlikely there would be large, intelligent creatures. The energy is probably too scarce, the pace of evolution too slow. But a functioning, self-sustaining biosphere of simple, microbial-scale life is a profound and real possibility. In other words, Titan presents us with a blueprint for a second, independent tree of life. A shadow biosphere that does not share a common ancestor with us, but is built from a completely different set of chemical principles. What this really means is that life in the universe might be far more clever and adaptable than we have ever given it credit for. It may not be limited to the narrow environmental niche of our water chauvinism. This journey to the strange, orange world of Titan marks the farthest limit of our direct exploration for now. We have found tantalizing hints of past life on Mars, and strong evidence for present-day habitable oceans on Europa and Enceladus. We have found a world in Titan that could host a form of life we can barely even conceive of, and all this possibility in our own solar system. Now, we must pull our perspective back to ask a more fundamental question about how life might travel between these worlds. Having journeyed to the far reaches of our solar system, from the dusty plains of Mars to the methane shores of Titan, let us now pull our perspective back. Let us rise high above the plane of the planets and look down upon the entire system as a whole, a collection of worlds spinning in the dark, each a potential island for life. We have been operating under the assumption that if life exists on any of these islands, it must have arisen there independently, a separate spark in a separate ocean. But what if that is not the case? What if life is not a series of isolated events, but a single, interconnected story? This is the central idea behind a concept known as panspermia. The word itself is ancient Greek, meaning seeds everywhere. It is the hypothesis that life exists throughout the universe, and that it can be distributed from world to world, and even from star system to star system. In this view, planets are not sterile islands waiting for a miraculous spark of their own. They are more like fertile gardens, waiting for a seed to be delivered on the cosmic winds. Imagine the solar system not as a series of separate rooms, but as a vast, interconnected archipelago of islands in a great dark ocean. The worlds are the islands, and the empty space between them is the sea. Now, imagine a storm on one of these islands, a violent cataclysmic event, like a massive asteroid or comet impact. An impact of this magnitude has the power to blast tons of surface rock out into space with such force that it escapes the island's gravity entirely. These ejected rocks, carrying with them the soil and microbes of their homeworld, would then drift through the ocean of space like natural rafts. For thousands, or even millions of years, these rocky rafts would tumble through the void. This journey is incredibly harsh. The rocks would be exposed to the freezing cold, the hard vacuum, and the intense, sterilizing radiation of space. Most any life clinging to them would surely perish, but the rock itself provides a shield. Any microbes trapped deep within the rock's porous interior, in a state of suspended animation, might just be able to survive. We know from our own planet that certain bacteria, called extremophiles, can enter a deep, dormant state, shutting down their metabolism almost completely and forming a tough, protective spore. They can survive incredible extremes of temperature, pressure, and radiation. They are nature's most resilient travelers. Eventually, after a long and random journey, one of these rafts might by pure chance wash ashore on another island. It would fall through the new world's atmosphere, its outer layers burning away in a fiery spectacle, but its core, and the microbial passengers within, could remain protected and cool. If this meteorite lands in a hospitable environment on the new world, a lake, an ocean, a warm patch of soil the dormant microbes could awaken. They could find the new garden fertile and begin to grow, to reproduce, and to colonize this new home. In other words, panspermia suggests that life is a contagion, a resilient cosmic seed that can hop from world to world. What this really means is that the various biospheres in a solar system might not be strangers but relatives. Life on Mars, if it ever existed, could have been seeded from Earth. Or, perhaps even more intriguingly, life on Earth could have been seeded from an earlier, warmer and wetter Mars. Some scientists believe Mars, being smaller, may have cooled and become habitable before Earth did, making it the more likely origin point. We may, in fact, all be Martians. This idea dissolves the neat boundaries we have drawn. The solar system becomes a single vast potential ecosystem, connected by the slow, patient commerce of falling rocks. It reframes our entire search. When we look for life on Mars or Enceladus, we are not just looking for an alien, we might be looking for a long-lost cousin. And the primary delivery service for these cosmic seeds would be the silent, icy messengers that have been wandering our solar system since its birth. To understand how these cosmic seeds might travel, we must now turn our attention to the most ancient and pristine objects in our solar system. We must follow the long, slow journey of a comet. These are not just chunks of rock and ice. They are time capsules, dirty snowballs that formed in the coldest, outermost regions of the solar system, far beyond the orbit of Neptune, in a vast, cold nursery of icy bodies called the Oort cloud. They are the leftovers from the construction of our planetary neighbourhood, and they have remained in a deep freeze for 4.5 billion years, preserving a perfect, untainted sample of the original materials that built our worlds. Imagine one of these comets, a small, dark, and irregularly shaped object, tumbling silently in the profound darkness of the outer solar system. For millions of years, its existence has been a quiet, uneventful orbit in the far cold depths. But then, A slight gravitational nudge, perhaps from a passing star or the distant pull of the galactic tide, disturbs its stable path. It is dislodged, and it begins a long, slow fall inward toward the distant, beckoning light of the Sunday. For centuries, for millennia, it travels inward, its journey marked by an immense and patient silence. As it crosses the orbit of Pluto, of Neptune, of Uranus, the Sun is still just the brightest star in the sky. But as it continues to fall, passing the orbit of Saturn and then Jupiter, the Sun begins to grow in size and intensity. The comet's surface, which has been frozen at near absolute zero for its entire existence, begins to warm. And as it warms, the ancient, pristine ices trapped within water ice, carbon dioxide ice, ammonia ice, begin to sublimate, turning directly from a solid into a gas. This process transforms the comet. The inert, dark chunk of ice and dust awakens. It begins to vent these gases, forming a vast, glowing, fuzzy atmosphere around its solid core, or nucleus. This atmosphere is called the coma. And as the comet gets even closer to the Sun, the solar wind, that constant stream of particles flowing out from our star, begins to push on this coma, blowing the gas and the fine dust particles that come with it into a long, magnificent and ethereal tail. We are now witnessing one of the most beautiful sights in the night sky. The comet has grown a tail, or, often two, tails, a straight bluish one made of glowing gas, and a gently curved white one made of dust. These tails can stretch for millions of miles, a luminous temporary banner painted across the blackness of space, and inside that tail, inside that glowing coma, is a chemical treasure trove. Spacecraft we have sent to fly through comet tails, like the European Space Agency's Rosetta mission, which orbited and landed on a comet, have found an astonishing abundance of complex organic molecules. They have found amino acids, the building blocks of proteins. They have found the chemical components of DNA. They have found pristine water, with a chemical signature that closely matches the water in Earth's oceans. In other words, these comets are not just beautiful spectacles, they are a cosmic postal service. They are delivering the fundamental prebiotic ingredients for life all across the solar system. For billions of years, comets and asteroids have been impacting the planets, delivering their cargoes of water and organic compounds. The very water you drink, the very carbon atoms in your body, may have been delivered to a young Earth by a comet just like this one. What this really means is that the raw materials for the garden are not just in the soil of the planets themselves, they are constantly being supplied from the outside. The solar system is a dynamic and interconnected chemical system. So, whether or not a living microbe could survive the journey between worlds, the basic non-living ingredients for life are almost certainly being scattered everywhere. Comets are the patient gardeners of the solar system, sowing the seeds of possibility on every world they touch. And this realization changes not just where we look for life, but what we are looking for. Our journey has shown us the incredible diversity of worlds in our solar system, each a potential habitat with its own unique chemistry and conditions. We've considered life hiding in the deep past of Mars, life thriving in the dark oceans of icy moons, and even life swimming in the cryogenic methane seas of Titan. But this raises a crucial, practical question. How would we actually know if we found it? What are we really looking for? We are searching for something scientists call a biosignature. A biosignature is any substance, object, or pattern whose origin specifically requires a biological agent. It is the fingerprint of life, a clue left behind that says, "I was here." It is not life itself, but the undeniable trace of its presence. These clues can be subtle, quiet, and easily missed, like a single footprint on a vast empty beach. Imagine you are a detective arriving at a scene. You are looking for evidence. The most direct and irrefutable piece of evidence would be a fossil. On Mars, our rovers are looking for microfossils, the preserved mineralized remains of ancient bacteria, perhaps trapped in the fine-grained sediments of that ancient lakebed in Jezero crater. Finding a single unambiguous fossilized cell in a Martian rock would be the ultimate smoking gun. It would be a definitive sign that life once existed there. But fossils are incredibly rare, even on Earth, a planet teeming with life. So we must look for subtler clues. We can look for chemical fossils or biomarkers. These are complex organic molecules that are known to be produced by life and are unlikely to be created by simple geology. On Earth, molecules like cholesterol or chlorophyll are excellent biomarkers. If we could find a complex, resilient molecule like that in a Martian rock sample, a molecule that has no plausible non-biological origin, it would be another powerful piece of evidence. We can also look for patterns. Life is not random, it is organized. It tends to create patterns and structures that are different from the chaos of pure geology. For instance, some microbes on Earth form large, layered structures called stromatolites as they grow. We are looking for similar, layered, textured patterns in Martian rocks that might suggest the action of ancient microbial mats. Life also has a preference for certain isotopes, different weights of the same element. For instance, life on Earth prefers to use the lighter isotope of carbon. If we analysed the carbon in a Martian rock and found it was unusually rich in the lighter isotope, it could be a subtle but profound chemical hint of past biological activity. And then there are the atmospheric biosignatures, the clues we can detect from a distance. We've already discussed methane on Mars, a gas that is out of equilibrium with the rest of the atmosphere and is quickly destroyed, meaning it must be actively replenished. On Earth, the most powerful biosignature in our atmosphere is oxygen. Our atmosphere is about 21% oxygen, a wildly reactive, unstable gas that would vanish in a geological blink of an eye if it were not being constantly pumped out by photosynthesizing plants and bacteria. Finding an abundance of oxygen in the atmosphere of another world would be one of the strongest possible signs of a living, breathing biosphere. In other words, a biosignature is the effect that life has on its environment. Life is a powerful geological force. It changes the chemistry of the rocks, the composition of the oceans, and the makeup of the air. What this really means is that we are not just looking for creatures. We are looking for the shadow they cast, the echo of their metabolism. It's a far more subtle and patient kind of search. It is a forensic investigation on a planetary scale, piecing together a story from the faintest of chemical and geological clues. And one of the most powerful ways we can look for these clues, especially on worlds far beyond our own, is by simply looking at the colour of the air. The search for biosignatures, these quiet fingerprints of life, has a beautiful and elegant method at its heart, one that allows us to study worlds we may never visit. It is the science of spectroscopy, the art of reading the messages hidden in light. It is a way of seeing the invisible, of deducing the composition of a planet's atmosphere from hundreds or even trillions of miles away. It is like looking at a candle through a piece of coloured glass. The light that reaches your eye is changed by the glass, and by studying that change, you can learn what the glass is made of without ever touching it. Imagine a single pure beam of white starlight, travelling through the vast emptiness of space. White light, as we know, is not one colour, but a perfect blend of all the colours of the rainbow to a complete spectrum. This beam of starlight is on a collision course with a distant planet. For a tiny fraction of its journey, it passes through the thin, gaseous envelope of that planet's atmosphere before continuing on its way toward our telescopes on Earth. In that brief, crucial moment of transit, something magical happens. The atmosphere acts like a chemical filter. Every gas in that atmosphere, oxygen, methane, water vapour, carbon dioxide, has a unique and specific property. It absorbs very particular colours or wavelengths of light. An oxygen molecule, for instance, will steal a very specific shade of red light from the passing beam. A methane molecule will steal a different set of colours in the infrared part of the spectrum. Each gas has its own unique barcode of colours that it absorbs. So, when the starlight emerges from the other side of the atmosphere and finally reaches our telescopes, it is no longer a perfect, complete rainbow. It is a rainbow with a series of very fine, dark lines missing from it. These are the absorption lines. And by carefully analysing which exact colours are missing, which lines are carved out of the spectrum, we can tell with incredible precision exactly which gases are present in that distant planet's atmosphere. The barcode of missing colors is a chemical fingerprint. This technique is how we know the composition of our own sun and of distant stars. It is how we first detected methane on Mars and the chemical soup in Titan's hazy sky. But its true power lies in looking even farther, beyond our own solar system, to the thousands of exoplanets we have discovered orbiting other stars. When one of these distant worlds passes in front of its star, from our point of view, an event called a transit, a tiny fraction of the starlight shines through its atmosphere. Giant telescopes like the James Webb Space Telescope are designed with exquisite sensitivity to capture that faint light and spread it into a spectrum. They are, in essence, giant golden ears, built to listen for the faint chemical whispers of alien air. What are we listening for? We are looking for a combination of gases that seems unnatural, a chemical mix that is out of equilibrium and hints at a biological source. We are looking for the great biosignatures. The dream scenario would be to find a planet with an abundance of oxygen and methane coexisting in its atmosphere. These two gases love to react with each other. In a dead geological atmosphere, they would quickly cancel each other out. To find them both in large quantities would be a powerful sign that some biological process is pumping both of them into the air, like our own planet's dance of photosynthesis and microbial metabolism. In other words, we are eavesdropping on the breath of other worlds. We are analyzing the collective exhalation of a potential global biosphere. What this really means is that our search for life is becoming an astronomical endeavor, not just a planetary one. We are no longer limited to the handful of islands in our own solar system. We are now capable of surveying thousands of distant shores, looking for the telltale colors in their air that might betray the presence of a living garden. And this vast, expanded search also amplifies a very old and very profound question. If the universe is so full of potential gardens, why do we only hear silence? As we expand our search from the handful of worlds in our own solar system to the billions of potential worlds in our galaxy, we are confronted by a silence that is as profound as it is vast. Our telescopes scan the skies, our radio dishes listen patiently for any signal that is not the random crackle and hiss of the cosmos, and the silence remains. This quiet, this apparent emptiness, is at the heart of a question known as the Fermi paradox. The physicist Enrico Fermi is said to have asked it in the 1952nd during a casual lunchtime conversation about the possibility of alien life. He listened to his colleagues' optimistic estimates of the number of stars, planets, and potential civilizations, and then he asked a simple, disarming question: where is everybody? Let us rephrase this question, not as a challenge, but as a gentle, meditative inquiry. Not, where is everybody, but why the profound quiet? Imagine you are standing on a remote, windswept beach at night, looking out over a dark, moonless ocean. You know that on the other side of this ocean, there are other continents, other cities teeming with life and activity. And yet, from your vantage point, all you can see is the dark water, all you can hear is the gentle rhythmic sigh of the waves. There are no distant city lights glowing on the horizon, no sounds of ships' horns carrying across the water. There is only the vast, deep, and patient quiet of the sea. This is our situation in the cosmos. The paradox arises from a simple, logical argument. Our sun is a typical, relatively young star. There are billions of stars in our galaxy that are much older, some by billions of years. It is overwhelmingly likely that many of these older stars have Earth-like planets orbiting them. If life is a natural outcome of chemistry on a suitable world, then some of these planets should have developed life long ago, and if some of that life evolved intelligence, as it did here, then those civilizations would have had a colossal head start on us. Thousands, millions, or even billions of years of technological development. A civilization with such a head start would, presumably, have explored and perhaps colonized its galaxy. Even at very slow sublight speeds, it would take only a few million years to cross the entire Milky Way. A few million years is a cosmic blink of an eye compared to the billions of years these older civilizations would have had. So, the galaxy should be teeming with signs of their existence. We should see their engineering projects, their probes, their signals. The night sky should be alive with their presence. And yet, we see nothing. We hear nothing. There is only the quiet. There is something deeply humbling in this silence. It is not an angry or menacing silence. It is a vast, calm, and indifferent quiet. It can be interpreted in so many ways. Perhaps we are simply not listening correctly, using the wrong technologies, or searching for the wrong kinds of signals. Perhaps they are here but are observing us from a distance, respecting a prime directive of non-interference. Perhaps they are so advanced that we are simply incapable of recognizing their existence, like an ant colony on the floor of the New York Public Library, completely unaware of the vast world of literature and information surrounding it. Or perhaps the silence has a more somber, more profound meaning. What this really means is that we are forced to confront the possibility that we have been profoundly optimistic. Perhaps some step in our story, some part of our journey from primordial ooze to sentient beings, is not common, but incredibly, vanishingly rare. The silence of the universe might be telling us something important about ourselves, about how precious and improbable our own existence truly is. It gently nudges us to consider the idea that our garden might not be one of many, but a unique and singular miracle. The profound quiet of the cosmos invites us to consider a sober and humbling possibility, an idea known as the rare Earth hypothesis. It proposes that while simple microbial life may be common in the universe, perhaps thriving right now in the hidden oceans of Europa or the icy rocks of Mars, the specific, long, and tangled chain of events that allowed for the evolution of complex multicellular life, like animals and plants on Earth, is an extraordinarily rare and improbable fluke. It suggests that our world is not a typical garden, but a cosmic jackpot, a sanctuary blessed by an unlikely convergence of fortunate circumstances. Let us walk through this quiet list of miracles, the gentle twists of fate that made our complex biosphere possible. We can start with our star, the Sunday. It is not just in the right place in the galaxy, away from the violent radiation of the galactic core, but it is also a remarkably stable and long-lived star. It is a G-type main sequence star, a Goldilocks star that burns steadily for billions of years, providing the long, uninterrupted summer that complex life needs to evolve. Most stars in the galaxy are small, cool, and volatile red dwarfs, which are prone to violent flares that could easily sterilize any nearby planets. Then, there is our planetary system. The presence of a giant like Jupiter, far out in the solar system, has been a crucial shield. Its immense gravity has acted like a cosmic bouncer, ejecting countless comets and asteroids that would have otherwise struck the Earth, causing mass extinctions that could have reset the clock on evolution time and time again. But perhaps the most important and unlikely feature is our relationship with our moon. Most planets either have no moons or a collection of small captured asteroids. Our moon is unique. It is enormous in relation to its planet, likely formed from a colossal impact in Earth's early history. This giant moon has been our planet's silent, patient partner, and its gravitational pull has done something miraculous. It has stabilized the Earth's axial tilt. Without the moon, the Earth's axis would wobble chaotically over long timescales, leading to wild, catastrophic swings in climate that would make it almost impossible for complex life to gain a foothold. Our moon is the anchor that has given us our stable seasons and our predictable, life-friendly climate. And the miracles continue on the Earth itself. Our planet has a strong magnetic field, generated by its molten iron core, which shields our atmosphere and surface life from the sun's harmful radiation. We have plate tectonics, a unique and dynamic geological process that recycles minerals, regulates the climate through the carbon cycle, and drives biodiversity by constantly reshaping the continents. This constant geological churning is a vital part of what has kept Earth's climate stable and its surface chemically rich for billions of years. Venus has no plate tectonics, and it became a runaway greenhouse. Mars has no plate tectonics, and it lost its atmosphere and froze. In other words, the recipe for complex life is not just add water and stir. It is a long and astonishingly specific list of ingredients and conditions. It requires the right kind of star, in the right part of the galaxy, with the right kind of planetary neighbours, a giant stabilizing moon, a protective magnetic field, and a unique geological engine like plate tectonics. What this really means is that Earth may not be a template but an anomaly. It might be the cosmic equivalent of winning the lottery a dozen times in a row. This idea is not meant to be lonely or discouraging. Instead, it can be seen as a source of profound wonder and gratitude. It reframes our world not as an ordinary place, but as a sanctuary of almost impossible preciousness. The silence of the universe, in this light, is not an absence, but a backdrop against which the song of our own living world becomes all the more beautiful and miraculous. But this entire line of thinking is still based on life as we know it, and perhaps the universe is simply more creative than that. We have spent our journey so far searching for reflections of ourselves. We look for water, for carbon, for the familiar chemical fingerprints of the biology we understand. We are like someone who has only ever seen paintings made with oil paints, and so travels the world searching for other oil paintings, assuming that all art must be made of the same materials. The rare earth hypothesis is the sobering conclusion that oil paintings may be incredibly rare, but what if the universe is not just a gallery of oil paintings? What if it is filled with sculptures made of light, with music carved from gravity, with forms of life so utterly alien that we are not even equipped to recognize them as being alive? Let us now step beyond the boundaries of our own chemistry and allow our imaginations to wander into the realm of pure but plausible speculation. We must redefine life itself, stripping it down to its most fundamental principles. At its core, any form of life must do three things. It must store information, it must gather and use energy to maintain itself against the forces of entropy, and it must be capable of replicating and evolving. On Earth, this is accomplished by DNA, metabolism, and natural selection. But are these the only tools the universe has at its disposal? Consider the element silicon. It sits directly below carbon on the periodic table, and like carbon, it can form 4 bonds, allowing it to create long, complex chain molecules, the potential backbones of an alien biochemistry. In a world much hotter than Earth, a world where water would instantly boil away, perhaps silicon-based life could arise. Imagine creatures with crystalline bodies, their biology based on the slow, high-temperature chemistry of molten silicates. Perhaps they would live on a tidally locked, hot-eyed planet close to a red dwarf, star, their blood a flowing lava, their breath a venting of sulfurous gases. Their metabolism would be incredibly slow, their lifespans measured in geological time. To us, they would appear to be living statues, indistinguishable from the rock around them, their thoughts as slow and patient as the cooling of a mountain range. Or let us go to an even stranger place. What if life does not require a planet at all? A star is a colossal, self-organizing system of plasma, governed by the elegant interplay of gravity and magnetic fields. Could some form of life arise within the fiery heart of a star? The physicist Frank Drake once speculated about life made of magnetic monopoles, forming complex, self-replicating structures within the plasma flows of a neutron star, living and thinking on a timescale of microseconds. Such a being would be to us as we are to the slow, patient life of a silicon creature. What about the vast, cold interstellar clouds of gas and dust where new stars are born? These clouds are suffused with a gentle bath of radiation and contain a rich variety of organic molecules. Could a form of life arise here, not as a discrete, bounded organism, but as a vast, diffuse, sentient nebula? A being of dust and gas, its thoughts the slow, gravitational eddying of its own substance, its consciousness spread out over light years. It would not be a creature in a place, but a creature that is a place. In other words, we are opening our minds to the possibility that life is not a noun, but a verb. It is a process, a pattern, a way that matter and energy can organize themselves to become complex and self-perpetuating. The specific medium carbon, silicon, plasma, dust might just be a local detail. What this really means is that the universe may be teeming with life, but it is life that is written in a language we do not know how to read. The silence of the Fermi paradox might be the silence of a library where all the books are in a language we have not yet learned to decipher. We are searching for prose, and the universe may be writing in poetry, in mathematics, in music. This journey into the speculative is not just a flight of fancy. It is a necessary act of humility. It reminds us that our search for life is not just about finding answers, but about learning to ask better, broader, and more imaginative questions. And it brings us back to a simple, fundamental truth. Whatever form life takes, it must be built from the materials the universe provides. And those materials, it turns out, are not rare at all. After wandering through the vast and speculative realms of truly alien life, let us bring our focus back to something more tangible, more fundamental. Let us return to the very ingredients of the garden. We have talked about the importance of carbon, of water, of organic molecules. For a long time, we wondered if the sheer abundance of these materials on Earth was another one of our planet's lucky flukes. But as our ability to look out into the cosmos has grown more powerful, we have learned one of the most hopeful and wondrous truths of modern astronomy. The building blocks of life are not rare. They are, in fact, woven into the very fabric of the universe. To see this, we must look beyond the planets and moons, and even beyond the stars themselves. We turn our gaze to the great dark clouds that drift in the seemingly empty space between the stars. These are the interstellar molecular clouds, the stellar nurseries, the places where new stars and new planetary systems are born. From Earth, they appear as dark, empty patches in the bright river of the Milky Way, like holes in the sky. But they are not empty. They are vast, cold, and surprisingly dense clouds of gas and dust, the raw material of creation. Imagine we are drifting inside one of these clouds, like a ship in a thick, dark fog. The temperature is just a few degrees above absolute zero. It is a place of profound cold and stillness. The only light comes from the distant, ancient starlight that filters through the dust, and the occasional, brilliant flash of a newborn star igniting in the cloud's deep interior. But this is not a sterile place. It is a cosmic chemical factory. Over millions of years, the simple atoms forged in the hearts of long-dead stars, hydrogen, helium, carbon, nitrogen, oxygen have gathered here. In the deep, shielding cold of the cloud, these atoms have begun to stick together. They cling to the surfaces of tiny frozen dust grains, which act as microscopic meeting places, catalysts for chemistry. And here, in the quiet dark, a slow, patient and magical process unfolds. The atoms combine to form simple molecules. 2 hydrogen atoms find an oxygen and form a molecule of water, which freezes onto the dust grain. A carbon atom links with 4 hydrogens to make methane. A nitrogen links with 3 to make ammonia. But the chemistry doesn't stop there. Bombarded by the gentle but persistent energy of cosmic rays and starlight, these simple molecules break apart and reform into ever more complex structures. We have pointed our radio telescopes at these dark clouds, and by listening to the specific frequencies of light they emit, we have found a veritable organic soup. We have found alcohols, sugars, and the long carbon chain molecules called polycyclic aromatic hydrocarbons. Most astonishingly, we have found amino acids, the essential building blocks of proteins, floating freely in the interstellar gas. Glycine, the simplest amino acid, has been detected in the material surrounding newborn stars. In other words, the process of creating the raw ingredients for life is not something that happens on planets. It happens in the vast, cold emptiness of space, before the planets are even born. What this really means is that when a new solar system forms, when a cloud like this begins to collapse under its own gravity to form a star and a surrounding disk of planet-forming material, it is already seeded with the essentials: the water in our oceans, the carbon in our bodies, the nitrogen in our air. These were not made on Earth. They were delivered to us, pre-packaged, from the interstellar cloud that gave birth to our Sunday. This is a profoundly beautiful and unifying idea. It connects our own existence directly to the great, cosmic cycles of stellar birth and death. The ingredients for the garden are universal. Every new star that switches on, every new planet that coalesces from the dust, is born into a universe that is already rich with the potential for life. The seeds are everywhere. The question is not whether the universe has the right ingredients, but which of the countless gardens are lucky enough to have the right conditions for those seeds to sprout. And this cosmic generosity is a truth we ourselves have tried to share, in a small, hopeful gesture sent out into the void. In the late summer of 1977, humanity did something quiet, hopeful, and profoundly human. We launched 2 robotic spacecraft, Voyager 1 and Voyager 2, on a grand tour of the outer solar system. Their mission was to be our eyes, to give us our first close-up views of Jupiter, Saturn, Uranus, and Neptune. They were scientific instruments of the highest order, but they carried with them something more, a cargo that was not a tool of science but a piece of art, a gesture of greeting. This was the Golden Record. Bolted to the side of each Voyager spacecraft is a 12-inch gold-plated copper disc. It is an interstellar message in a bottle, a time capsule from our world, intended for any civilization that might, in the distant, unfathomable future, find these silent, drifting messengers. The decision to include it was not a scientific one, but a deeply philosophical one. It was an attempt to answer the question, if we could tell another civilization one thing about ourselves, what would we say? Imagine the small team of people, led by the astronomer Carl Sagan, tasked with this impossible and beautiful challenge. They had to distill the entire human experience, our science, our art, our music, our diversity, our feelings onto a single phonograph record. What would you choose? What sounds and images would you select to represent all of humanity? On the record's gleaming golden cover are a series of simple, elegant diagrams, a kind of cosmic instruction manual. There is a map of our solar system, a diagram of a hydrogen atom to provide a universal unit of time and distance, and most poignantly, a pulsar map, a diagram showing the location of our Sun relative to 14 known pulsars, a celestial address that would allow a sufficiently advanced civilization to pinpoint the record's origin in space and time. And the contents of the record itself are a symphony of our world. There are 115 images, encoded in analog form, showing scenes of life on Earth, the structure of DNA, a human fetus, a nursing mother, children of all races, a sunset, the Great Wall of China, a supermarket. There are the sounds of our planet, the wind, the rain, the crashing of waves, the chirping of crickets, the calls of whales and birds, the sound of a kiss, the laughter of a child. There is a collection of greetings, spoken in 55 different languages, ancient and modern, beginning with Akkadian, spoken in Sumer about 6,000 years ago, and ending with a simple, hopeful hello from the children of planet Earth. And then there is the music. The team tried to capture the breadth of human musical expression, from Bach and Beethoven to Chuck Berry's Johnny B. Good, from the panpipes of the Solomon Islands to the blues of Blind Willie Johnson. It is a mixtape for the cosmos, a selection of the sounds that move us, that give our lives meaning and beauty. The Voyager probes completed their planetary missions decades ago. They are now travelling in the dark, silent space between the stars, moving at over 35,000 miles per hour. They are the fastest, the most distant objects humanity has ever made. They will not come close to another star for 40,000 years. The chances of them ever being found are infinitesimally small, but that was never really the point. In other words, the Golden Record was not truly a message for aliens, it was a message for humanity. It was an exercise in self-reflection, a way of holding a mirror up to ourselves and asking what is most important, what is most beautiful, what is most worth preserving about our time on this world. What this really means is that the Golden Record is an act of profound optimism. It is a testament to our deep, innate, and perhaps universal need to connect, to reach out, to say, "We are here." It is a quiet, hopeful whisper, sent out into the great, cosmic silence. And it is a legacy that we are continuing today, with new tools that are more powerful than we could have ever dreamed. The golden age of exploration that the Voyager probes began continues today, but with a new generation of explorers, both robotic and telescopic, each more powerful and sensitive than the last. Our search for life in the solar system and beyond is accelerating, driven by technologies that are pushing the very limits of what we can see and what we can know. The future of the search is not a distant dream. It is happening right now, and it is poised to make discoveries that could reshape our understanding of our place in the cosmos. Looking inward, within our own solar system, a fleet of new missions is being planned to follow up on the tantalizing clues we have already uncovered. For Mars, the next logical step after the Perseverance rover's sample caching is a Mars sample return mission. This is an audacious, multi-stage plan, a kind of interplanetary relay race. A new lander will touch down near Perseverance's cache, a small fetch rover will gather the sealed tubes, and a rocket the first ever to launch from the surface of another planet will blast that precious cargo into Mars orbit. There, an orbiting spacecraft will capture the sample container and begin the long journey back to our world. Within the next couple of decades, we may be holding pieces of a Martian river delta in our laboratories, able to study them with a precision that no rover could ever match. Searching for the definitive fossilized fingerprint of life. For the ocean worlds of the outer solar system, the plans are even more daring. NASA's Europa Clipper mission is already under construction. It will not land on Europa, but will make dozens of close, low-altitude flybys, using a powerful suite of instruments, including ice-penetrating radar, to map the thickness of the ice shell, confirm the existence and depth of the ocean, and even analyze the material from any plumes it might fly through. It will be the Great Reconnaissance mission, creating a detailed map of a habitable world. Following it, we dream of a lander, a robotic probe that could touch down on the surface, perhaps near one of the reddish cracks, and drill down into the ice, sampling the pristine layers just beneath the irradiated surface, looking for the chemical building blocks of life that may have been brought up from the ocean below. And looking outward, beyond our solar system, the game has been completely changed by the James Webb Space Telescope. This magnificent instrument, a giant golden honeycomb of a mirror floating 1 million miles from Earth, is the most powerful time machine ever built. Its incredible sensitivity to infrared light allows it to peer through the dusty clouds where stars are born and to analyze the faint light of the most distant galaxies. But one of its primary missions is to do exactly what we discussed, to capture the starlight filtering through the atmospheres of exoplanets and to read their chemical barcodes. The Webb telescope is our first true tool for atmospheric reconnaissance. It is the giant golden ear we are using to listen for the breath of other worlds. It is already studying the atmospheres of gas giants and is beginning to probe the air of smaller, rocky, Earth-sized worlds orbiting nearby red dwarf stars. It is searching for water vapor, for methane, for carbon dioxide. It is looking for that telltale mix of gases that is out of equilibrium, the potential biosignature that could give us our first credible evidence of a living world beyond our own. In other words, we are moving from an era of speculation to an era of data. Our questions are becoming testable hypotheses. What this really means is that we are living in a unique and privileged moment in human history. We are the first generation that has the tools to seriously and scientifically answer the question, are we alone? The discoveries of the next few decades, from the rocks of Mars, the plumes of Enceladus, and the atmospheres of distant exoplanets, have the potential to be the most profound in the history of science. And this entire outward-looking quest has a strange and beautiful side effect. It inevitably forces us to look back at ourselves. As our journey has taken us farther and farther from home, a quiet, circular pattern has begun to emerge. The more we learn about other worlds, the more we inevitably learn about our own. The search for alien life is also, and perhaps more importantly, a search for ourselves. Every question we ask about Mars, or Europa, or a distant exoplanet, is a question that holds a mirror up to Earth. When we study the dried-up riverbeds and the thin, cold atmosphere of Mars, we are forced to confront the fragility of a planet's climate. Mars is a cautionary tale, a ghost of a world that lost its magnetic field, lost its atmosphere, and lost its water. It teaches us that a habitable world is not a permanent condition, but a delicate and precious balance that can be tipped. Studying the history of Mars's climate collapse helps us to better understand the forces that govern our own climate, the fine-tuned engine of oceans, atmosphere, and geology that keeps our own world stable and alive. We look at the red, dusty ruin of our neighbour and feel a renewed sense of urgency to be better stewards of our own blue and green garden. When we dream of the hidden, sunless oceans of Europa and Enceladus, we are inspired to look with fresh eyes at the most extreme and unexplored environments on our own planet. The discovery of life at hydrothermal vents in our own deep oceans was a direct result of wanting to understand how life could exist in such alien conditions. The search for life on other worlds has driven us to discover life in places we never thought to look on Earth, in the super salty brines of Antarctic lakes, in the rocks deep within the Earth's crust, in the clouds high in our atmosphere. We are still discovering the limits and the resilience of our own biosphere, a quest driven entirely by our curiosity about others. When we analyze the chemical barcodes in the atmospheres of distant exoplanets, we are essentially creating a field guide to planetary evolution. We see young, hot Jupiters and ancient, rocky super-Earths. We see worlds with thick, hazy atmospheres like Titans and worlds that may have lost their atmospheres entirely. This cosmic menagerie of planets provides a context for our own. It allows us to see the story of Earth not as a singular, isolated narrative, but as one possible outcome among an infinity of others. It helps us to answer the question, what makes a planet like Earth? By showing us all the ways a planet can be not like Earth. In other words, astrobiology is also a profound act of self-discovery. It is the science of understanding our own context. What this really means is that the search for life in the universe is a deeply humanistic endeavour. It is driven by the same fundamental questions that have haunted our poets, our philosophers, and our spiritual leaders for millennia. Where did we come from? What is our place in the grand scheme of things? And are we alone in our feelings of wonder, of awe, of loneliness? The quest is a journey not just to other places, but to a different perspective. It is an exercise in cosmic humility, a way of seeing our own world, our own lives, and our own problems through a wider, more compassionate lens. And there is no image in the history of our exploration that captures this transformative power of perspective more perfectly than a single humble photograph taken by a distant, departing friend. Our journey is now coming full circle. We have travelled to the farthest reaches of our solar system and peered out into the interstellar dark. Now, we begin the long, slow return trip home. To do so, let us join one of our most faithful messengers, the Voyager 1 spacecraft. It is now February 1990. The spacecraft has completed its breathtaking tour of Jupiter and Saturn. Its primary mission is over. It is now hurtling towards the edge of our solar system, on its way to the great empty space between the stars. It will never return. Before its cameras were to be shut down forever to conserve power, the astronomer Carl Sagan, a guiding spirit of the mission and of our entire journey tonight, made a special request. He asked the mission team at NASA to turn Voyager's camera around one last time and take a final picture of the worlds it was leaving behind. It was a sentimental request, not a scientific one. From Voyager's incredible distance, nearly 4 billion miles away, the planets would be just tiny points of light, holding no scientific detail. After some debate, the command was sent. Voyager paused, turned its gaze back towards the heart of the solar system it had called home, and took a series of 60 photographs, a final family portrait of the Sun and its planets. Among these images was one that focused on a tiny, almost insignificant speck of light. In the final photograph, our entire world, every continent, every ocean, every mountain, every city, every single living thing, every person who has ever lived, appeared as nothing more than a tiny pale blue dot, suspended in a single scattered ray of sunlight. It is a humbling and profoundly moving image. Let us float here for a moment, in the silence of deep space, and simply look at that dot. Consider the rivers of blood that have been spilled by generals and emperors so that, In glory and triumph, they could become the momentary masters of a fraction of that dot. Consider the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great, enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbour life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. In other words, this simple picture is a lesson in perspective. It is a silent, cosmic sermon on the folly of human conceits. What this really means is that astronomy, the act of looking out, is a deeply humbling and character-building experience. It underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. This perspective does not provide us with a final answer to our question. It does not tell us if there is life elsewhere, but it changes the emotional tone of the question itself. The search is no longer an arrogant quest to find lesser beings or grand galactic civilizations. It becomes a gentler, more humble search for companionship, for a sign that we are not alone in this vast, dark ocean. It becomes a search for a reflection of our own fragile, precious, and beautiful aliveness, and this brings us to a place of peaceful acceptance. After this long and winding journey, after visiting the ghosts of Martian rivers, the hidden oceans of icy moons, and the shores of methane seas, after contemplating the great cosmic silence and gazing upon the humbling image of our own distant world, we arrive not at an answer, but at a place of calm and gentle acceptance. We must come to terms with the beautiful and perhaps permanent uncertainty of our quest. We may not find a definitive answer in our lifetimes, or in the lifetimes of our children, or ever. And that is perfectly okay. The true gift of this search is not the destination, but the journey itself. The question, is there life in the solar system, is like a beautiful winding path that leads us through the most wondrous landscapes of science and imagination. Following this path is what enriches us. The striving to know, the patient act of looking, the collaborative and multi-generational effort of sending our robotic envoys out into the dark, these are the things that elevate us. The search itself gives us a sense of purpose, a grand and noble story to be a part of. Imagine the search for life not as a hunt, but as an act of listening. We are standing on the shore of that dark, cosmic ocean, and we have placed our ear to a seashell, listening for a faint, distant echo of a song that may or may not be playing. The act of listening is, in itself, a form of connection. It is an act of hope, of reverence for the mystery. The value is not in whether we hear the song, but in the fact that we have learned how to listen with such incredible patience and sensitivity. We have built our beautiful intricate shells, our rovers, our orbiters, our telescopes, and we are holding, prove them up to the universe, in a state of quiet and hopeful attention. We can find a deep sense of peace in this state of not knowing. Uncertainty is not a void, it is a space of infinite possibility. In that space we are free to wonder, to imagine, to dream. Mars might be sterile, or it might be holding the fossilized secrets of a second Genesis. Europa's ocean might be a dead chemical soup, or it might be home to a thriving dark biosphere. The silence of the galaxy might be the silence of absence, or it might be the silence of a language we do not yet comprehend. All these possibilities can coexist peacefully in our minds, a rich tapestry of maybes, a vast and wondrous ocean of possibility. There is no need to rush to a conclusion. The universe is ancient and patient, and we are just beginning our conversation with it. We can let the question rest gently in our awareness, like a smooth, cool stone in the palm of our hand. We can feel its weight, its texture, its mystery, without needing to break it open to see what is inside. In other words, the search for life is not a problem to be solved, but a mystery to be lived. We can inhabit the question, finding comfort and wonder in its unanswered depths. What this really means is that our place in the cosmos is to be the observers, the listeners, the storytellers. Our role is to witness the majesty of the universe and to appreciate the profound, beautiful, and perhaps singular miracle of our own conscious awareness. And this brings us to the final step of our journey tonight. We have travelled billions of miles across decades of scientific discovery and into the farthest reaches of our imagination. Now, it is time to complete the journey home, to bring our awareness back from the vastness of space and into the intimate, immediate, and undeniable presence of the one life we know for certain. We begin our final, gentle descent. Let your awareness pull back from the pale blue dot, that distant, lonely speck. We cross the vast, quiet gulf of space that separates the outer planets from the inner. We glide past the orbit of Jupiter, a silent, swirling giant, and cross the ghost-like wilderness of the asteroid belt. We see the rusty light of Mars ahead, and then pass it by, drawing ever closer to the brilliant blue and white jewel of home. We approach the Earth now, not as a tiny point of light, but as a world. We see the familiar, beautiful continents, the deep, shimmering blue of the oceans, the soft, swirling patterns of the clouds. We enter the atmosphere, that thin, precious membrane of air, and the black of space gives way to the familiar, comforting blue of the sky. Our descent continues, through the high, wispy clouds of ice and down into the warmer, denser air below. Let your awareness drift down, over the landscapes of our living world. Over the great green canopies of the rainforests, the vast golden expanses of the savannas, the silent white majesty of the polar ice caps. Let it drift over the cities, with their intricate geometric patterns of light, and over the quiet, dark countryside. Your awareness is coming home, back to this continent, this country, this town, this very room where you are resting now. Bring your attention from the cosmic to the intimate. Feel the gentle weight of the blanket upon you, the softness of the pillow beneath your head. Notice the quiet rhythm of the air in the room, the subtle ambient sounds of your own peaceful space. The entire, grand and sprawling story of the cosmos, of suns and planets and the search for life, has led to this one, simple and miraculous moment. The moment of your own quiet, conscious presence. This is the one piece of the universe that you can know, with absolute certainty, is alive, the life that is you. Consider the sheer, staggering improbability of your own existence. The unbroken chain of survival stretching back over nearly 4 billion years, from the first fragile, self-replicating molecule in a primordial sea, through countless generations of microbes, of sea creatures, of strange and wonderful animals, all leading to you. Every one of your ancestors for 4 billion years successfully survived long enough to reproduce. It is a lineage of such profound tenacity and luck that it borders on the miraculous. Feel the life that is humming quietly within you. Feel the slow, steady and effortless rhythm of your own breathing, the air moving in and the air moving out. Each breath is a quiet metabolic fire, a gentle exchange with the world, the same fundamental process of energy conversion that powers every living thing. Feel the gentle, rhythmic beat of your heart, a faithful, tireless muscle that has been pumping the river of life through your veins since before you were born. The warmth of your body is the warmth of a slow biological flame. The thoughts drifting through your mind are the product of the most complex structure we have yet discovered in the universe, the human brain. You are, in this moment, a living, breathing, feeling, and thinking piece of the cosmos. You are the universe made aware of itself. The stardust that forged in the heart of ancient suns has learned to wonder, to love, and to dream. It has learned to ask the question, am I alone? In other words, you do not need to look for life in the oceans of Europa or the dust of Mars to experience a miracle. You are the miracle. The simple, profound, and undeniable fact of your own aliveness is the most powerful evidence of life you will ever encounter. What this really means is that the answer to our great cosmic question is not out there, in the dark. It is in here, in the quiet, warm, and breathing presence of your own being. For tonight, this is the only answer you need. We have returned now, fully and gently, to the quiet sanctuary of this room. The grand tour of the cosmos is complete, and we are left with the soft, warm stillness of the present moment. We began our journey tonight with a simple question, whispered out into the vast, dark courtyard of our solar system. Are we alone? We travelled to worlds of red dust and hidden oceans, chased the ghosts of water and the whispers of methane, and found not a single, simple answer, but a far more beautiful and enriching tapestry of possibilities. We found that our own garden, the Earth, is a place of rare and specific miracles. It sits in a gentle sunlit zone, a perfect distance from our star's steady campfire. It was gifted a giant stabilizing moon, and it churns with a hidden geological fire that has kept its climate and its life in a state of dynamic balance for eons. Our home is a sanctuary, perhaps a very rare one, but we also found that the conditions for life might not be so narrow as we once believed. We journeyed to the cold outer darkness and found, beneath the frozen, fractured ice of Europa and Enceladus, the astonishing promise of vast, warm and chemically rich oceans of liquid water. These worlds taught us that the warmth of a star is not the only way to make a garden grow. The patient, rhythmic pull of a giant planet can create its own secret, life-giving hearth in the deep. We visited the strange, orange-hazed world of Titan and stood on the shore of a methane sea. This hauntingly familiar landscape, carved by a liquid and shrouded in a thick atmosphere, challenged our most fundamental assumptions. It asked us to imagine a form of life built from a different chemistry, a weird life that thrives in a cold that would freeze our own biology solid. Titan taught us that the universe may be more creative, its definition of life more flexible than we have ever dared to imagine. So, where does that leave us? Are we alone? The question now feels different. It feels softer, less urgent. The solar system, we have learned, is not a collection of dead, sterile rocks. It is a place of immense and surprising potential. It is filled with water, with complex, organic molecules, and with sources of energy. The ingredients for life are not the exception. They are the rule. The seeds of the garden, it seems, have been scattered everywhere. We may still be the only world where those seeds have grown into a complex conscious biosphere. Or we may be one of many gardens, most of them small, hidden and microbial, thriving silently in the dark. We do not yet know, and for tonight, that is a beautiful place to be. We can rest in the quiet magnificence of the mystery, content with the journey and at peace with the unanswered question. The search will continue, the patient listening will go on, but our part in it, for now, is done. We can let go of the wondering and simply be. For tonight, we can find our rest not in the answer, but in the quiet beauty of our own living, breathing world, this one precious garden that we know and that we call home. And in the profound, simple miracle of our own quiet, sleepy and wondrously alive selves, sleep well.